Okay, good morning, everyone. On behalf of the organizing committee, it's my great pleasure to welcome you to the Multi-Modal Spatial AI, the Multi-Modal Spatial Intelligence for Robust Navigation and Open World Understanding at ICRA 2026. Thank you all for joining us today. We are very delighted to see researchers, students, and industry practitioners to join us today and to discuss one of the most exciting topics in robotics and embodied intelligence. Today's spatial AI for robotics is undergoing a remarkable transformation. For decades, robots have relied on carefully designed perception, localization, mapping, planning, and control subsystems. At the heart of many robotic systems, and closely related to our workshop, are the spatial perception and SLAM. Over the years, we have witnessed tremendous progress in filter-based and fact graph optimization-based state estimation methods. These approaches have enabled robots to navigate complex environments with accuracy, robustness, and reliability. And they have become the cornerstone of modern robotics. At the same time, we are witnessing the rapid rise of foundation models, large-scale multimodal learning, language action models, and word models. These advances are fundamentally reshaping how machines perceive, understand, reason about, and interact with the physical world. In the context of spatial perception, feed-forward 3D models have attracted enormous attention in recent years, with breakthroughs such as Dust3R, Master3R, Slam3R, and VGT, etc., demonstrating new possibilities for localization, reconstruction, and scene understanding. The term spatial AI has gained significant momentum in recent years, yet it carries different meanings across different communities. For some, it means the next generation of SLAM, 3D viewing, and state estimation. For others, it serves as the key building blocks for embodied AI, VLAs, and world models. This naturally raises a number of fundamental questions. Will localization and mapping remain core components of next-generation robotic systems? How should geometry, semantics, language, and action be integrated into a unified representation of the physical world? And perhaps most importantly, what role will spatial AI play on the path towards the general-purpose robotic intelligence? Today's workshop provides a unique opportunity to foster dialogues about these questions. Before we begin, let me briefly give an overview of this workshop. We are fortunate to have 7 distinguished keynote speakers, 33 accepted papers. Among them, there are 12 are selected as the audio presentations across our morning and afternoon sessions. We are fortunate to have 4 sponsors, and we will recognize the best paper and best poster awards with 1 additional finalist for each category. We are honored to host an outstanding lineup of keynote speakers, including both the world-renowned senior researchers and the rising star junior researchers. Our keynote speakers include Professor Andrew Davison from Imperial College London, Professor Dezhen from MM-SpatialAI, Professor Margarita Chli from ETH Zurich and University of Cyprus, Professor Alex Wong from Yale University, Professor Hermann Blum from University of Bonn, and Professor Timothy Barfoot from University of Toronto. And Professor Sebastian Scherer from CMU. I would also like to take this opportunity to thank our amazing fellow organizers who have provided great support in making this workshop happen, including Yafei Hu, Lucas Schmidt, Yang Kim, Stephen Lloyd-Nager, and Guchuan Huang. I would also like to sincerely thank our program committee members for their valuable support in promoting this workshop and reviewing paper submissions. We are also very grateful to our sponsors, including Nocom, AgileX, DeepMirror, and ATAX. For a detailed agenda of our 4-day workshop, please visit our webpage by scanning the QR code. We will have, for this morning session, we will have invited talks, followed by our first session of the contributed paper oral talks. And we don't have the QA sessions for these oral presentations. Instead, we will recommend the discussions in the coffee and poster sessions, just following the oral presentations. And then we have some other invited talks. In the afternoon, we will start from 2 o'clock, and we have the invited talks, and also our second contributed paper, oral talks. Our sponsor introduction, the panel discussion, award ceremony, and the closing remarks. Yeah, with that, thank you all for being here. I hope you will enjoy the workshop, engaging in the fruitful discussions, and finally, leave with new ideas, new collaborations, and new perspectives. With that, let's get it started. That's firstly, Professor, we will have our keynote speaker, Professor Andrew Davison, to give us a keynote talk. Okay, Andy, you can set up your presentation. I will have a quick introduction of Professor Andy. Andrew Davison is a professor of robot vision at Imperial College London. His long-term research focus is on SLAM and its evolution towards general spatial AI. With his collaborators, he has constantly developed breakthrough systems, including mono-SLAM, Kinect viewing, SLAM++, IMAP, and Gaussian splatting SLAM. Recent prizes include best paper at ECCV, the Helmholtz Prize at ICCV, and best demo at the CVPR. He has also taken his technology into real applications, including the Dezhen vacuum cleaner and as co-founder of SLAM Core. He was elected Fellow of Royal Academy of Engineering in 2017 and Fellow of the Royal Society in 2023. Okay, let's welcome Professor Andrew Davison.
Good morning, very good to be here, and thanks for the invitation. Yes, I'm going to talk to you just a bit about, you already mentioned spatial AI, and my views about what that means and what the interesting research challenges are at the moment. But let's just remind ourselves a bit where some of this research has come from. So I've actually been working in this area of SLAM for a very long time, since the mid-90s. This was, I think, the day that I submitted my PhD. So I built a visual SLAM system for this robot with stereo cameras, and it was a sparse visual SLAM system that was able to make maps of a room like this. So this is the estimated trajectory of a robot moving across the room. This was the map that it built of sparse visual landmarks. So you can see maybe 20 or 30 landmarks in a room. So together with odometry, that was enough to enable quite accurate localization within that room. And at that time, using standard cameras for SLAM was a very new thing. Most other implementations in the 90s were not using cameras at all. But I kind of realized that cameras could be very useful and important, partly because cameras are cheap, they're general. But I think even then had this kind of view that cameras, they're the same sort of visual sensors that humans and animals have, and there's no real upper limit to what you can get from cameras. It's not just geometry. You can get all this information about what's in the world as well. You can recognize people. You can understand the semantics of scenes as well. So we weren't doing it then, but I think that even at that point, a large reason to try and do things with cameras was because of that. So what I tried to do since my thesis work was to really generalize that capability to not require a special robot with a stereo active head. Could we do all of that just with a single camera? And in 2003, we published MonoSlam, which showed that you could do real-time single camera SLAM. So again, it was still a sparse map of features, really a map that enabled localization and not more. But that was already quite enabling. And then in years since then, we've really been trying to build up levels of representation. So towards the end of the 2000s, we were working on dense SLAM. So this means could we use a camera to recover not just sparse maps, but really detailed 3D geometry. And this was enabled by new processing becoming available, especially from GPUs. So we published things like DTAN and Connect Fusion, showing that in real time with single sensors, you could build reconstructions that look like this, where you can really see the shape of things. But this is still geometry. What we really need is more like meaning of objects in order to do really smart things with them. So some work that we did on that, this was back in 2013. So we called this an object-oriented SLAM system. So this was a paper called SLAM++. And it's the same setup, it's just a camera moving through the world, but now with some quite strong prior information that we expected the world to be made up of certain types of objects. So in SLAM++, we had really specific prior information. We had 3D CAD models of the objects that we expected to be present, like these chairs and tables. So if we're in a room with lots of exact replicas of the same object in different configurations, we could recognize those objects, we could fit the 3D models, and then we could represent a whole room just by the layout of these objects. So each one of these objects only needs 6 parameters for 3D pose in order to define it, and then we need one copy of the model of each one of these objects. So that's a map which it's dense. We can use it for localization, but it's also semantically useful. We can we could do planning with this map. So we know what we can do with a chair and what we can do with a table, for instance. On the other hand, we can see that it has this quite specific prior assumption needed, that we needed to know the shape of the object in advance. So that's clearly a limitation. So I'll just show you something that we've done very recently, which I think fits into the same kind of area as SLAM++, in that we're trying to make an object level representation of the world. We know, of course, from deep learning, we had really strong pre-trained models that can look at images and pretty much turn images into object-like chunks. So in this paper, super primitives that we published 2 years ago, it's the same kind of setup as that we're going to have a single camera moving through the world. But we're using some off-the-shelf pre-trained networks here. So one network that segments an image into object-like chunks. So we're using something like the SAM network that can take any image like this and find object-like chunks. And then we're using another network that does some sort of local reconstruction. So in this paper, we were actually using a normal prediction network that can look at an image and predict the orientation of the normals at every pixel, and then we can locally integrate up those normals into the shape of the objects. But in this case, we had some ambiguity because we didn't know the overall scale and size of the object. So we didn't know whether this was an object which is small and close to the camera or big and far away. But that's a problem that we can easily solve multi-view. So now that we have a moving camera and we've got multiple images, we've got these different hypotheses for this object of whether it's small and close or big and far away. And we check those by projecting them into the other image and finding which of those hypotheses is the most closely consistent. And then if we do that for all of the objects, we can get this object level reconstruction. So of course, these chunks that we get from SAM are not necessarily the exact objects. So for instance, a chair may be turned into multiple chunks. So some objects will be over or possibly under segmented. But still, we've got this, really good high-level breakdown of the scene into chunks. And then our SLAM-like reasoning is just figuring out where the chunks are. And because these are pre-trained models, we haven't trained these ourselves. They've been trained on each data. They work on all sorts of different scenes. So here we've got a SLAM system that's estimating the motion of the camera and then the 3D positions of all of these. And that is actually a really useful representation, I think. So the latest thing we've done in that line, we were just going to present at ICRA next week, is a version of the same kind of system that is now also applied to scenes that have motion in them. So if we're looking at a multi-view view of a scene like this that has independently moving objects, we apply the same process of splitting each image into chunks using off-the-shelf segmentation and local reconstruction. And then what we are really showing in these visualizations is that we can then register all of the images together. So let's say that we are applying some 3D model to try and understand this scene that has motion in it. You may be used to seeing things like this, where at each frame we have a different reconstruction because the object has moved. But because we have segmented this into chunks, and we can actually match those chunks over the sequence, we can actually reconstruct the scene in this non-rigid way. So it's like that each one of these chunks will have a separate motion estimate, and then we can put all of those together. And we can also do clustering to say that nearby objects probably have similar motion. That's our kind of starting assumption. So we can do things like this. We can track a set of objects together, and even when they become invisible, so we've only got one camera here looking at the front of the drawer, but we can make this pretty good guess that these objects that were moving together when we can see them will stay moving together even when they become invisible. So we've got this kind of idea of yeah, is that a good idea?
Do that. Yeah, here's another example on a commonly used sequence in computer vision. Yeah, and here's a nice one. So we put a carton of milk into the door of the fridge. We're tracking everything here, the door and the object, and then we close the door, and we can see that the milk is moving with the door. Even when the milk becomes invisible, we still kind of guess that that's what's happening. So now we can sort of look at an X-ray view inside the fridge and kind of get a good idea that the fridge is still there. So this makes me think of these kind of theory of mind experiments that people do with young children, where they ask them, when a person leaves and goes out the door, for instance, where are they? I remember my kids being very confused about that when they were small, but it's something that humans are very good at. so far this is, not really robotics. We're not doing anything with this. Let me show you one other example where we have actually done some robotics with these object-like scene representations. So this is a slightly older system than the previous one, but we were working on going beyond specific CAD models in this work. So here the idea was we do have prior knowledge of specific objects we expect to find in this scene, but rather than being a specific CAD model for each one of these objects, we have like a variable shape space model. So for instance, we've trained a 3D generative model on thousands of 3D models of mugs. So now when we see a new mug in the scene, we've got a low dimensional shape space that we can optimize to fit the shape of that specific mug. So now you'll see, again, a SLAM-like system built out of this. We're estimating the motion of the camera. When we identify and detect new instances of these objects that we know about, we bring in this shape model and we optimize the parameters of the shape model and the position of the object. This is another example. So we're going to move the camera around this circular table and basically make a 3D map of the objects here that have really quite accurate geometry. So you'll see that when each new object is detected, it appears in the 3D map, and then you'll see there's some multi-view optimization that the shape and position of the object will be gradually adjusted to become more accurate. So we've got here a robotic example of something that we can do with this. So here we've got a camera mounted on the wrist of this robot arm. We're going to take some views of this scene, fit and optimize these 3D shape models so that the robot hasn't seen these specific objects in its training set, but it's seen a whole lot of things that are similar to them. And now basically this is like our digital twin of this real scene. We've got quite accurate geometry here. So then we can do some really simple planning. It's just off the shelf motion planning to then pick up the objects and not just kind of drop them, but place them precisely. So we'll stack the bowls in order and then place the cups in neat positions in here. So this is all enabled here by quite explicit 3D geometry. I think I'm going to skip this. So let's keep going. So where's this all going? So that early visual SLAM work that you saw is really out there in many different sorts of products. Some of them are robots, some of them are not robots. But what are the products that I think probably most of us are dreaming about? These probably really world-changing products, like really general home robotics. Of course, there's many companies now making great advances on that. Or another big application area I think is kind of personal AI. So you might think of something like that. This is Meta Project Aria. It's a prototype of really lightweight glasses that you might wear that would in general keep track of everything that's going on and kind of augment your intelligence. So these are really tough things to build. No one yet has really made these things work convincingly, I would say, and that's especially due to the really tough constraints. Things like size and weight. In a product like this, you've got massive constraints on power usage that are really tough if you want to make them small and lightweight and have good battery life. And then safety, for instance, with robots and humanoids, I think is still a huge challenge. So lots of people are working on that. So let's come back to this term spatial AI. The way that I've defined it, and in fact this was defined back in 2018 in this paper that I wrote called The Computational Structure of Spatial AI Systems. Probably the first time that the term spatial AI was used in this particular context. So there I defined it as the online problem where vision is to be used, usually alongside other sensors, as part of the artificial intelligence, which permits an embodied device to interact usefully with its environment. So a very general definition, and I think clarifying that I always thought that what we were doing in SLAM was building up to this. I was interested in building representations of scenes that enable intelligence. Localization and navigation is one early part of intelligence, but there's all the rest. So I always thought that by building up these levels of representation, we were building representations for intelligence. So of course, there's a lot of debate about this at the moment. Does embodied AI or robotics need explicit scene representation at all? So we see all this work on things like vision, language, action models that just say, we're not going to build a map of the scene. We're just going to have a neural network that takes in images and predicts actions. And of course, we must kind of assume that somehow implicitly within a network like that, there is some representation, but it's all going to be somehow a black box that we don't understand. Of course, what we're hearing a lot more about recently is this concept of world models. So this is a term used in machine learning. In my mind, it's saying we do think that we need persistent representation of scenes, but we're not going to try and design it. We're just going to have some sort of set of parameters, weights that will learn the properties of the scene that allow us to predict what will happen in the future. But we'll feed in new images, things we want to do into the world model, and it will predict what happens. So that is a scene representation, and you could argue, there's two ends of a scale where how do we represent this scene? We have this purely sort of implicit world model, or we have something much more explicit, like the kind of things that I've shown you, where we might have a graph of objects which enable an explicit planning. So, neither of these approaches really works well yet, I would say. We're going to see tons of things in this conference of progress, but, these products do not exist yet. There's nothing like a robot that can do all the jobs you want in your home in anything like how a human can do. And I think my guess is where we'll end up is somewhere sort of in between these approaches. So there are many, many advantages of the more explicit approach. It's very, very modular. It's very efficient. You can sort of cut and paste within it. You can do all those sorts of things. You can easily bring in new classes of models. We've got all this kind of well understood machinery. On the other hand, there's massive advantages of more implicit models as well. So I think we're going to see tons of work on that. I think the specific aspect of all of that, where whatever the representation is, I've become very interested in the computational structure. So I think in any of these approaches, we accept that we're going to have there's going to be continuous streams of data coming in from sensors. So I've only really talked about cameras here. I know this is a workshop about multimodal spatial AI. So that information could come from many types of sensors. But I think crucially, we're going to have this sort of loopy computation. There's going to be an area of memory in our system that's representing the world. A map or a world model or whatever it is probably going to have some modular graph-like form. And then we're going to have this stream of data kind of going round and round. Every new image that comes in has got to be used to update that representation. New decisions will come out. Maybe there'll be information from lots of other sources. So this is just a very rough sketch of the sort of computation graph of some of the systems I showed you earlier. I mean, the point I wanted to make is it's complicated. It's also pretty inefficient at the moment. So the kind of demos we've built have been running on desktop PC type of systems. There's a lot of stuff running on CPU, a lot of stuff running on GPU, whether that's the neural networks or whether it's certain elements of dense reconstruction and matching. So one of the things I'm very interested in is what will computing hardware be like in the future? And I believe we're at the beginning of a a massive change there. So we've been through the era of doing everything on CPUs. So for 20 years of my work, or maybe 15, we were just using CPUs. Of course, in the last 10, 15 years, we've been using GPUs as a primary processor. So they're very parallel processors. They're incredibly useful, but they weren't originally even designed for AI. They were designed for graphics, and they've been adapted. There are certain workloads they're really good at, but others that they're not that good at. And I think we're going to see a whole load of hardware designed specifically for robotics and AI coming soon. And I think the most important thing that I kind of come back to is, if you want to be efficient, the thing that's expensive in computing hardware is moving memory around. That's the thing you want to avoid doing. So that argues for kind of co-locating processing and memory. So the sort of processor that I think will happen is, it's got lots of little independent computing cells that have local memory, and then those cells will all communicate with each other in a sort of message passing way to keep the whole thing consistent. And maybe that's in general more brain-like. So I would argue we might have something like the spatial AI bit of lesson. If processors are going to become like that, we should think of designing algorithms that are ready to work with that sort of thing. So start giving up on the idea of having blocks of global memory. We need to think in a more graph-like way. So that's my kind of bet at the moment. So there are companies that are already making chips that are more like this. This is an example from a company in the UK called GraphCore, where they think of the computation that has to happen in some system, and they almost kind of map it geographically. They take the computation graph and map it geographically down onto their chip that has many processing tiles and local memory. I've been thinking a lot about this sort of graph-like structure, the kind of geographical layout, if you like, of the algorithms that we use in spatial AI. So this comes from the future mapping papers, or it's also discussed in the last chapter of the SLAM handbook that's now coming out. So yeah, how can we find this graphical nature? And then if we want this to work in general, so we use factor graphs still as our main kind of engine, but neural networks also are graphical models, but basically. And then I've worked a lot on kind of old algorithms actually recently, but so belief propagation and Gaussian belief propagation. It's an algorithm that you can use to do factor graph inference in a purely local way. So rather than like building big matrices and stuff like that, you pass messages around graphs. And we've been really studying the properties of that and trying to understand, can we do a lot of these computations in spatial AI in a very distributed way by passing messages around graphs. And Gaussian belief propagation has this distributed convergence property. So we've done things like implementing bundle adjustments on a graph processor by passing messages around the tiles of a processor. We've been looking at things like, how do we take what starts as a complicated graph and gradually try and simplify it by, for instance, identifying objects and grouping them into simpler structures. And then a current project that we're very interested in is on-sensor vision. So again, if we're really interested in efficiency, we don't want to move data around. Robots of the future will probably have many cameras. Can we push as much of the processing as possible that we need to do in computer vision actually pretty much into the cameras? So there are prototypes from teams, for instance, at the University of Manchester, and there's a lot of this kind of stuff going on in industry as well. So cameras that basically have processing built into the pixels. It's a bit like an evolution of the event camera type idea into much more programmable per pixel processing. So how much computer vision can we do actually in the pixels of a camera, where each pixel has a little bit of processing capability, some local memory, and then the ability to talk to its neighbors or possibly some further away pixels. And I again think that these belief propagation style algorithms that work very, very locally might enable us to do really efficient computer vision right there in the pixels, and then a camera would not send out video. It would send out something much more abstract. Okay, so I need to finish. The last thing that I'm very interested in recently is multi-robot systems, and this has really come from when we're using distributed algorithms. We can use those across the tiles of a single processor, or we can also use them across multiple robots. So I don't have much time to go into this, but in future systems where we may have many robots occupying the same spaces, we can use the same sort of distributed algorithms to do things like distributed localization and distributed planning. So there are some references here if you're interested in that. Okay, so just to conclude, I think spatial AI, these really difficult applications, they do need persistent scene representation. I believe that. I'm quite agnostic about what the actual scene representation should be, but I think a really crucial question that we maybe don't hear talked about so much is what's the kind of overall structure and computational layout of these algorithms, and then how will that fit with the hardware that's coming soon. Okay, so I'll finish there. Thanks very much.
So, see, we can have one quick question to the limited time. Please.
Thank you for the talk. You showed quickly a slide about master slam, so it's very interesting work. Could you very briefly describe what it is about?
Yes. So apologies that I skipped through that one. So master slam is it's a dense slam system that works with a single camera that's going to build a real-time dense map of a scene. So we're using here again an off-the-shelf pre-trained model. So master is this work from Naval Labs. It's one of these kind of 3D geometry foundation models that can take in 2 images and build a local 3D point cloud. So in this system, we're using that as a kind of module. We've got a camera continuously moving around. We're making these local reconstructions, and then we've got a fairly kind of standard SLAM pose graph backend that's stitching all of those local reconstructions into a consistent map. So I would say, this is one of, there are many pieces of work like this happening at the moment. Of course, there's newer versions of models like master, things like VGGT or depth anything or Pi3 that can now take in many images in one go and build a 3D representation. But again, I still think that SLAM-like ideas are very useful here. If we want to have a genuine real-time system that can make a growing and changing 3D representation of the world, we can't just keep taking every image that we've ever got and feeding it to a foundation model again and again. We need something that can update and change incrementally and kind of adjust as we get new information and loop closures and things like that. So Master Slam's a system that has that kind of property. But yeah, like most people, we're astounded at how good these 3D reconstruction foundation models are these days.
Let's thank our speaker again.
No? Good morning, can you hear me? Hi, Xingxing, can you hear me?
Hello, can you hear me?
Hi, Des, can you hear us?
Yeah, now I can hear you.
Oh,
Yeah,
sorry, I cannot hear you.
can you hear me now? Can you hear me? Sorry, can you hear me? Check.
Hey, Des, can you
Do you
hear
have
us?
a?
Oh,
Yes,
I'm
I can
sorry,
hear you.
we
Can you hear?
cannot hear you.
Can you hear
Uh,
me? Do you have your speaker enabled?
hey, test.
Test, 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 test.
Hello?
Can you hear me? Hello, hello,
Uh,
hello, hello. Let me think. Hello, can you hear me? Okay.
can you hear us?
Yes, I can hear you. Can you hear?
Oh, I'm sorry.
Hear
Let me
can
try.
you hear me now? Yes. Can you hear me?
Yes, yes. Okay, you can start your presentation now.
Okay, great. Thank you. I really wish I could be there with you guys. My name is Dezhen. I'm a professor at MBZUI. Today I want to share a work we have done actually during the pandemic. This is actually received more relevance during the recent geopolitical conflict. So the work I'm going to present is called Proprioceptive Localization. You can simply imagine it as a blindfolded localization. So what I mean is when you have a whiteout or a whiteout situation in a snowstorm, and also you lose the GPS signal actually at this particular moment we lose a GPS signal in Abu Dhabi at the city scale from time to time because of the geopolitical conflict. Um, are you still able to localize yourself when you drive a vehicle on the road? Or so this has become a interesting problem. But we have think about what is the minimal information you would need to address problem like this. Of course, this fall into the traditional category of localization to solve the problem for where am I. I'm not looking for a complete scene reconstruction because it's impossible for such a situation. But still, we need to know where we are. Most time, we will have a uh, the proprioceptive sensor like IMU or even the wear encoder. Potentially, you also have access to the campus, so digital campus. Those are the minimum set of sensors. But you might also have the pre-storage map as a prior. Are you able to drive and figure out where you are? So here, this is basically the theme of today's talk. So we have three different algorithms with increasing robustness. But I will focus mostly due to time limit. I would most focus on the first one, and then I briefly touch the second and third algorithms. So the first algorithm, we actually very straightforward. So it's you are given this minimum configuration of sensors. You assume you can drive around and make turns and then generate a sequence of heading changes. Are you able to just localize yourself on the map without any extra information? So that's what we call the PLAM algorithm. And this particular algorithm require you to have access and prior downloaded map of the city. But you have to drive according to traffic rules, and you don't have longitudinal motion. The map itself is an urban map, so mostly it contains strike segments, and there's some limitation with respect to these assumptions. We will talk about this at the end of this session. Of course, this inevitably will think about the variant-related localization and also some of the existing work on campus-based navigation. But these algorithms, some of them still rely on the recognition of landmarks. One of the characteristics of algorithm today is we're not going to require you to recognize landmark and register yourself to the landmark. You're doing the sequence matching, the sequence generated from the proprioceptive sensor and the sequence that you can find on a pre-processed map. So this is actually much more robust because we don't rely on external landmarks. Okay, so this particular algorithm has three components. The first component is called heading graph construction. This is just corresponding to Andy's talk earlier. This is actually a special type of scene representation for this particular localization purpose. Then we have query sequence generation and localization inferencing. I'm going to start with the heading graph construction. So given a prime map, static map from the city, so it's typical examples are the Google Maps, OpenStreetMaps. You have a road level GPS waypoint, based map. We process this into something called a heading graph, with a vertex to be we call the there's vertex to be defined as the long straight segment or short transitional segment. So vertex has a single orientation or single heading in particular, and also it has edges that corresponding to either road intersections or curve segments. So the example here you can see is in this street corner, you can see there's a curve segment that be treated as a edge instead of a vertex. And the 1, 2, 3, 4 are the four vertexes that from the straight segment. And also we have intersection, the two red arrow indicated the graph that link the between the nodes that create an edge that's just corresponding to the edge. Constructing this graph is actually a per GPS waypoint based algorithm. If you're familiar with OpenStreetMap, you know that it consists of a set of rows, and each row is a collection of waypoints. We process them segment by segment. Of course, we do coverage estimation on those rows and to figure out are they straight segment or the coverage segment. We create a special label function. So the label function is really just help us determine should we divide a long road into several segments, each of them corresponding to a vertex, or should we keep them all together? So the details, I won't bother you with the details. Just let you know this labeling function is to serve that purpose. So when you have this heading graph generated, I'm just go for each vertex, you can estimate its orientation easily because that's a simple line fitting, and you get the heading of this vertex, and that will give you the information you need, and also you have starting point and end point of the vertex. So the orientation distribution is important to point out. The orientation is not just a single value. This is a Gaussian distribution because it depends on how many waypoints you have, and from state estimation, it's not that difficult to obtain it, given the set of at least the square you have, or simply estimate that you can use. For generating the query sequence, relatively straightforward. Just take a EKF output from the IMU, and you're tracking the heading, and you're looking for the stable heading segment from when you're driving around, and this will allow you to extract a signature heading sequence. We do not pay attention to the transitional component. We only look at the stable heading segment. So this will generate a query that we needed to use to query the heading graph previously defined. So in this particular example, the key thing is how do you get locations through the query sequence. Of course, for any query sequence, we know the length. Usually, length is n. It's increasing, and as you're driving, when you make a turn, each time you are changing your heading, you increase your sequence length. But you also can sample the candidate sequence from the graph. You can matching the candidate sequence on the graph with the query sequence. Each individual, essentially, is individual matching is a hypothesis testing. But in order to make the whole sequence match, the entire hypothesis testing has to be successful, right? So basically, this is the localization problem become a sequence of hypothesis testing problem. But the key question is whether this localization scheme will converge. Are you able to get a true location over a relatively large map or over a degenerate map? So to analyze this, we can simply treat this, this is a typical Bayesian process. So we have the events, the joining event that all this sequence, the mean value of orientation corresponding to each other, and also with that condition, what is the probability the true it is a true match overall. It's a true match. But deriving on this, we actually obtain a result in this lemma. But I don't want to bother you with the detailed process. I just want to remember the localization speed is actually determined by a factor of 1 minus alpha times kd divided mb. What does that mean? Alpha is really a small probability threshold for the hypothesis testing, usually 0.05. And the KD essentially is all possible heading directions in the map. Just like essentially KD, if KD is large, it means the map is relatively chaotic. And MB is actually all the potential neighboring directions when you add a particular node. So what does that mean? Is if your map is completely rectilinear, that means you will have all possible directions equal to all possible neighbors. That means you're going to have this value will be less than 1. If it's less than 1, you take the power, which every time you increase the number of observations, you take the power, that means its probability will not increase. If it's not increasing, that means you're not having a converging situation. So it is actually not surprising that the result that if you have a pure rectilinear map, this algorithm would fail. But how many maps are actually rectilinear? That's actually a question related to the value of these algorithms. So we take a look at in fact, we are looking at did it's called entropy analysis on all the maps from the world. We actually take the top 100 cities and actually from the US from the OpenStreetMap at time. So we calculate the entropy. Essentially, it's a distribution of the potential directions of all these segments. We found that most city it's actually supermost majority of city has entropy. It means actually the 75 out of 100 has an entropy greater than 0.0. And only 5 out of these 100 cities has less than 0.60 entropy. So this is actually a very good we actually put that together as a histogram, become the distribution we use to analyze and or use in simulation analyze the potential successful rate of this algorithm in a general city. So to do that, we can use that to simulate all cities with this entropy distribution to see the successful rate and the efficiency of these algorithms. So we start with a simulated experiment. Basically, what happens is we're using this prior distribution we obtained of the entropy and use that to drive the simulation generation. So if it will give you an idea, so to generate an entropy from 0.6 to 0.99, let me show you the range of the data. You can see as time goes, this map gets more and more irregular because entropy increases. Okay, so it will stop at 0.99, which is relatively chaotic map in this case. So we use this generator. We can test the algorithms and to see how well it can converge. So we can arrive at the result as this. It is a graph with the vertical axis as number of solutions. Of course, the more solution you have, more chaotic. You want the solution to be 1. That means you're correctly localize yourself. And then you also have the y-axis, the end number of observations. You would like to have less observation, which means you make less turns. You can figure out where you are. And then there's entropy on the other axis showing how likely to become successful. So the red zone you're looking at, the red plane, is actually the convergence zone. It's a place of the localization success. So basically, if the entropy is greater than 0.9, which is 75% of the city, you can localize yourself in slightly above 10 turns. If you drive making 10 turns, you will localize yourself successfully because you converge to a single solution. So With this in mind, we also did the physical experiments. We did with both Kitty map and also the College Station, Texas map. So in these testings, the both map has a relatively high entropy, about 0.95. And so the convergence was not a surprise. On averages around the converge slightly less than 10 turns. That actually very well fit to the simulation analysis. I agree with that. Also, I want to give you a typical localization scenario. If you look at the middle part, we have a right side to be vehicle trajectory, left side to be vehicle trajectory, right side to be the location inferencing. So if I play this video, you can see the vehicle driving. At the beginning, it's many green dots, has many potential solutions. And when they start moving around, the number of green dots decrease. Until see if a video playing successfully, it converged to a single dot. Let's see. It's a bit slow over the network. Let's see if the video. Okay, so basically, this algorithm works, but only for about the 75% of cities. So there's limitations. It is very hard to localize vehicle in a degenerate map. That's because you only use head information. Localization only intermittent for turns. You cannot localize exact position if you're not making turns. So also, if entropy is less than 0.6 in some map, you will never converge, right? So what are we going to do? A natural solution is to incorporate the distance traveled. We call it graph-based, proprioceptive localization. In this particular algorithm, we added the distance, the trajectory information, but it's actually not as trivial as you would think, because it's common to think about, okay, well, have more information, should converge fast, and it should be more robust, right? So, but there are a couple challenges. One challenge is vehicle trajectory not necessarily fit to the road map. If I give you this particular example on the right side, you can see this the road map is very lousy. It's a road level map, not a land level trajectory. Also, there's two vehicle trajectories showing up here, trajectory 1 and trajectory 2. They are very different, but they're all correct trajectories. But if you're doing a brute force matching, it's not going to match very well, because they're not the. Imagine you also have very big drifting noise over time, right? So this is not going to give you a nice matching of time. So we have spent a lot of time to deal with this, but the key questions is to address the global localization. So I'm going to skip some part that is similar, structurally similar to the previous work, and only focus on the some of the key component. The global location, and also be able to matching toward the between the trajectory and the map itself. So okay, let me just so constructing the heading graph become the construction of a heading length graph, adding the length information, one more dimension. That's no big difference. Generated query is also not much of a difference. You pull out more information from the EKF, and that's it. But then you have the distance, the travel of each segment. But this distance traveled, although it is not exactly the row segment, but it's a query point. So we're going to generate a query sequence to become the heading sequence and the distance sequence together. So now the graph matching become, you not only you have to match the heading, you also have to match the distance side. You can still treat this as hypothesis test, but the difficult part is the distance path matching is not a simple one-to-one matching like the heading matching. But what's we really compare the convergence analysis between this and the previous work. It is because you have a distance component, it actually we can prove that it's always converging faster than using heading alone, which is not very surprising because you have more information. But on the other hand, be able to mathematically prove it is also a rewarding experience. So a lot of effort is really spent on how to deal with this trajectory mismatching. So that means you have a trajectory does not really matching with the road because of the way the vehicle is driven. Right? The vehicle can change lanes. We can make a curvature turn, and those are all cause a lot of trouble in these making algorithms. So we actually spend a lot of time to figure out how to figure out the virtual starting stopping point, so we can have a proper distance, and we also have to think about how to just using longitudinal information and to compensate for vehicle odometry error. We call the scale and the sleeping factor. And this is other things that that's too much weeds. I don't want to go into them, but I will just give you. You have to trust me. We get this problem solved, and we're able to matching this. But the one of the result I want to show you is this. Let me just go to here. Compared to the the previous, this is the previous graph I showed, the vertical axis number of solutions. Again, you can see the converging zone, the red zone for the new algorithm, GPBL is PL is a lot bigger than the previous algorithm with the distance information. Keep in mind, all these are relative travel, so we're not too sensitive to the drifting, but from the convergence analysis, we can converge in around about 7 turns, and in this case, LCT is about 0.0 in entropy. Successfully, we can successfully localize ourselves in a simulated map situation, and it can deal with most of the linear situation as long as each district is not exactly the same size. So there's still some degeneracy, but that's much less restrictive than the previous work. So I'm not going to go into details on this due to time sake, but I want to move to the next work. There's still have one thing we haven't addressed. There's just this algorithm's strong dependence on the trajectory types. So let's give an example. If you drive like straight line, you don't make turns. So that means your n does not increase. But what about in this scenario? How can you localize yourself? Of course, in a desperate situation, you can change your trajectory, drive along road, help yourself to find out. What if I tell you you don't have to? If there's many vehicles running the same algorithm, we can do a vehicle-to-vehicle collaborative localization. And that's essentially the last part of this work. So basically, what happens is you can help by if you are ego vehicle. In this case, we have ego vehicle. You can exchange information with vehicle in your neighborhood. In this case, we're assuming this is a close range communication. The vehicle you're encountering that can exchange information with you actually are on the same street or same intersection. You're not talking to a vehicle like that you cannot see. It has to be direct line sight and also pretty close to you. So what that happens is you can exchange your belief functions. You can merging the graphs together. You have a quick convergence rate. But for this method to work, you have to analyze, kind of inspired by other people's collaborative localization work. You have to analyze the rendezvous event. So whenever you run into other vehicles, there are different types. So what do we mean by that? Is in the different rendezvous event, you could be co-located in the same vertex. You're driving same direction on the same road. You're very close to each other within communication range, or you could be in coupled vertex. By coupled means you are on the same street but different directions. And here is a V7, V8. Or you are in intersection sharing. You basically are in the same intersection. So those are the potential rendezvous type of event. For each of these events, it will dictate the different way of combining the graph together. Then you can start after combining graph, you can start query all together. They will converge more faster. Similarly, let me just skip the key part is when you do this, the multi-vehicle belief function, your exchange belief function has a very nice property. I'm going to go into that is once you analyze it, or can give you a result is it will be definitely faster than the single vehicle localization case. Of course, the corner case would be you never ran into any vehicle, you degenerate yourself into a single vehicle localization, which is a GPPL algorithm. And in this case, your speed is exactly the same as the GPPL algorithm. So the convergence rate is the same. But once you encounter other vehicles, your convergence rate is much faster than others. So this is kind of a nice result to have. And when during the tests, actually we kind of tested two type of driving strategies because they resemble the two extreme cases. So what do you mean by extreme cases? One is random walk. Whenever you drive to an intersection, you're taking a random direction, random left and right or straight, in equal probability. Or you drive on the same street, you never change. So what are those two representing means that all other driving behavior is somewhere in between. That's the why we're using those driving behavior as test example. So in the simulation, we have we test them those with a city with a lot of vehicles driving around. So we perform random walk or we perform on the same street. So the interesting part, if you take the pie chart of the rendezvous events, there the distribution of rendezvous events is kind of similar. You have about 30 a third of them will become is a type 2, and it means the intersection sharing, and third of them being the type 0 that's on same street, and the sort of a little bit over a third is being type 1, which means you are sharing so you run into each other in opposite directions. That's kind of the distribution. This testing situations, and we know that random walk is a very very favorable for localization, so it never fails. So there's no failure rate percentage in the random walk. But in the straight line driving, you can see it's a map of the failure rate percentage. That means you can see the number of vehicle increase in the city, the failure rate decrease. At the beginning, if there's nobody on the city, there's very few vehicle on the city, you don't run into them, you have very high failure rate because the algorithm depends on your trajectory. If you don't make turns, it is very difficult for you to localize yourself, so it fails. But when you run into other vehicles, other info share the information with you, gradually you're getting more information. So in fact, your converging speed also goes faster. So this is actually very favorable. And also with the city having 1,000 vehicle on the road is not a very big number at all. So if we look at we also did the experiments on the physical experiments, and the result is kind of conformal to the analysis, similar to the simulation results. So I'm not going into detail, but in general, this type of work is very useful for you handle the situation in a blindfolded localization setup, and they'll help you, especially have a vehicle to find its location. This work was mostly done by my former PhD student, Jasmine Chen, and she never had a chance to present this work in conference due to the pandemic period. All this work was done in pandemic period. So today is actually the first time I've ever presented this line of work for my student. That's all. Thank you.
Okay, thank you, Daz. And we can have one quick question due to the limited time. Yeah, feel free to come to the microphone if you have one question. Okay, I have a quick question for Daz. With the emerging 3D foundation models, how do you think the foundation models can play a role in the proprioceptive localization?
I think I would think about the merger situation. So that means you don't need to rely on constant reconstruction of the environment, of full environment, because it's costly. If you incorporate proprioceptive localization into this, then you can reduce your computation to a periodical computation that you can save a lot of reconstruction. So you don't have to constantly perform to calculate things. Yeah. The robustness can be increased. Of course, here we don't even talk anything about the landmarks and situation like that, but you could put some back, just like how do we develop an algorithm can gracefully degrade into the proprioceptive localization when everything else fails. And also gradually pick up more information as when things start recovering, right? So this is the kind of thing will be more robust for the future environment. As a researcher, we tend to pick up a single problem to work on, but from application perspective, have a combined approach, be able to fall back at the necessary steps or go increase complexity and when the condition allows, is something that we can always think about. Yeah.
Okay, thanks. Let's thank our speaker again. Yeah, thank you.
Thank you.
Hello, everyone. Let's get back to our next keynote talk. Yeah, please get seated. Okay, guys, let's get back to our next keynote talk. Please find your seats. Thank you. Okay, great. It's my great pleasure to introduce our next outstanding speaker, Professor Margarita Chli. Margarita is a professor of robot vision and director of the Vision for Robotics Lab at the University of Cyprus and Zurich. Her work has contributed to the first vision-based autonomous flight of a small drone and the first demonstration of collaborative monocular SLAM for a swarm of drones. Margarita has delivered valuable keynote talks at the World Economic Forum in Davos, TEDx, and ICRA. She is the co-chair of the IEEE IS Technical Committee on Computer and Robot Vision and serves on Cyprus National AI Task Force, advising the government on AI policy. Let's welcome our speaker, Professor Margarita Chli.
Great. Thank you very much for the introduction. You didn't have to say everything. So it's nice to be here. Hi, everyone. My name is Margarita Chli, and I'm going to talk about robust perception for single and multi-robot systems and how far along are we. I usually like to start my talks with these videos. Probably you've seen them before. I really like them. Why? Because they show, like this example here, this eagle is spotting salmon through water and it's able to plan its path and reach out and grasp it while they're both in motion. And so this is an excellent example of planning, control, perception, all coming together to do something that is, seamless for nature and very difficult for robotics. So what is it that we need to build into our robots to make capabilities like this happen? So this is one question for one robot, and for multiple robots, how could we have them coordinate and collaborate without crashing into each other and hopefully doing something useful together? So the big question here is, what kind of situational awareness and perception perception capabilities do we need to build into our robots to make things like this happen? And I like to take these big questions and big question and break it down into three naive, smaller sub-questions that I think we need to be tackling and we're working towards in the lab. So first of all, I think we need high fidelity SLAM to get this awareness of space for our robots. And then once we have this, we want to work towards a denser, richer scene representation that is going to basically help us with the autonomy that we want to build in, to interact with the robot, with the environment, to reach out and grasp something, or to plan a path to complete the pipeline of autonomy. And if we do have systems, robotic systems, that they are able to do high fidelity SLAM and intelligent scene representations, then why not have multiple of them collaborating and coordinating to do something useful all together? So I'm going to go through these challenges one by one, and I'm just going to show you some recent results and some ongoing thoughts that I hope you find interesting. So high fidelity SLAM, right? So many people think that SLAM is solved. So unfortunately I wasn't here in the first half of the workshop to be able to see what you have seen. But many of us, even in the community, do say that SLAM is solved, right? And some of you might think about that. So okay, take your favorite SLAM system that you have in mind. I'm going to show you one example. Here it is. As a downward-looking camera onboard the drone, using basically one camera and one inertial measurement unit, running keyframe-based SLAM. And take your favorite and think whether you can employ it to do path planning, to do dense reconstruction for plug-and-play purposes directly. And where I'm going with this is that in order to capture a video like this, 2 minutes of autonomy, we need to be on the site a few hours, days in advance to choreograph what we were about to be doing, to see whether our systems initialize properly. So yes, your favorite system, my favorite system, they're all SLAM systems, but are they high fidelity? And what is it that we're missing? At the lab in Cyprus and in Zurich, we're working primarily with vision, right? And with vision-based navigation, we have some great things like visual cues and appearance, and we have some very bad things like visual appearance. So here's one example of a student project that the idea here was that we were trying to detect these small moving aircrafts, small because they're long range, while we're both in motion, the camera and the moving target. So this was a Yellow 11 based architecture, trying to extend it to detect objects in sequences of images instead of single images, aiming to have lightweight implementation. So what are the problems? Problems that we all have in vision. Low contrast between the object and the background, ambiguities, we think we saw the object, we think we haven't seen the object. So basically this drives us to look into more things than just vision. And we started looking into LiDAR inertial odometry. So what you are seeing on the top left is this sensor head that we are currently working with. It has cameras on there, a LiVox LiDAR, and the aim here is to be able to track in darker scenes and track more dynamic motions. And what you're looking at here is my postdoc Rowan. He's shaking the sensor suite camera. I'm used to saying camera. He's shaking the sensor suite and trying to make it break. It will break eventually. So what's running in the background is LiDAR inertial odometry, and in fact is Ellipse Leo. He's presenting it at a workshop down the corridor here, which is basically a method for adaptive LiDAR inertial odometry with an ellipsoid representation. So what makes this as robust as you've seen are three key contributions. First of all is the adaptive scan filtering. So we need to downsample data, or LiDAR-based systems need to downsample data. How can we do this without losing important information? So the aim here is to have as generally a uniform distribution as possible, no matter how far the scan lines are from you, but also favor denser data around the sensor because we have higher fidelity in this sensor data. So what is being achieved here is that as opposed to a fixed downsampling distribution, we have an adaptive distribution, adaptive downsampling that's based on the environment, the sensor resolution, and the field of view, which results into better capture of the local geometry, basically. Then we have this ellipsoid representation where we are mapping LiDAR points into higher level primitives, ellipsoids, that can be one of three shapes: linear-like ellipsoids, planar, and balls. Okay, so then mapping each such LiDAR point to the ellipsoids means that we can have these higher level primitives that can help us avoid outliers, but at the same time we have a fidelity score on these ellipsoids to see how well they represent the local environment. So again, that's one other key thing, to have a better representation of the local geometry for improved robustness to matching. And finally, we explicitly target matching to older LiDAR points, because we know that this is about drift correction, and we also try to avoid areas where we know that we have degenerate LiDAR degenerate regions, to downgrade matching there, and this brings better basically drift correction than existing approaches, as you see here. So with these three key contributions, Ellipse Leo is basically a very adaptive system, so you can try out if you like. And what Rowan is showing here in this graph is the best performing settings for every algorithm that we compare against, with Ellipse Leo having basically we don't really change anything. So what you see there as a resolution is the maximum possible resolution, but it always stays constant across different data sets. And maybe if you can focus on this video that is played 10 times the speed, the idea here is that we have a very challenging sequence where the sensor is navigating through a very narrow corridor and going down the stairs and coming back up to close the loop. And this adaptive scan filtering and the ellipsoid representation is really the two key things that help Ellipse Leo survive while other methods diverge. Now, even if you have the best vision-based SLAM system and the best LiDAR-based SLAM system, you still might want to fuse the two. So how can you fuse these sensing cues? And in traditional SLAM, we do discrete time SLAM. We approximate the ground truth with a set of discrete motion estimates using constraints that are coming from our favorite sensors: visual, LiDAR, inertial. And of course, the big problem here is that we are essentially approximating what's happening in between these estimates, right, with a straight line. So if you want to track your drone that's flipping, or something more interesting is happening in between your motion estimates, then you're not able to capture it accurately. So moreover, sensor syncing becomes very important. You either deal with it in optimization, or you deal with it on the hardware side, which makes your sensor much more expensive. So the community and us as well have been working towards continuous time SLAM to basically have a continuous time representation of the scene, for example, of the trajectory, for example, using splines or Gaussian processes. So again, it's an approximation to the ground truth, but the idea here is that you have an estimate of where you think your sensor suite has been at every moment in time, and you have the ability to tweak a little bit, for example, your spline bases, to optimize them according to what your sensors say, even if these sensor readings come in an asynchronous manner, for example, using an event-based camera. So the support for asynchronous sensing here can come for free. And so with this in mind, we were thinking that what if, instead of having a monolithic time horizon window that you carry with your latest data, and you're trying to optimize within that window, why not just optimize your trajectory in places where you know it's exceptionally uncertain? So what if we could be selective on which parts of the trajectory to optimize? And what if we could assess which bases of your spline to optimize based on their covariance estimate? And this is the main idea behind this system that my student called Hyperion. Is a bit of a pompous name, I'm sorry for that. But the idea is that we are proposing to do continuous time SLAM in a Gaussian belief propagation-based optimization, which means that updates can be triggered asynchronously from robot states that they are more uncertain and propagated along your graph accordingly, basically. And this offers decentralized probabilistic inference and covariance estimation for free. So we've run this on simulated data, and we're hoping that at some point this is going to become possible with real data. So to zoom back out, for this first challenge on high fidelity SLAM, I've bombarded you with information on experimenting with deep learning, with vision, with LiDAR, with trajectory representations. Why? Because we want to achieve estimates about where the robot is, the pose, and the map of the environment. And so far, the map I've assumed that is rather sparse, which brings me to the second challenge, on scene representations for interaction and path planning. I'm not going to stay here for long because I want to focus more on the multi-agent collaboration, but just to show you a taste of what it is, of the kind of questions that we are working on at the lab. So on the top right, you see Orb SLAM running, feature-based vision SLAM, visual SLAM. Then we are densifying each scene and mapping all of that in a denser scene representation using Gaussian splatting, which is basically representing the scene with a set of bubbles, Gaussian bubbles, which the lovely thing about this is that from certain viewpoints, this representation looks very photorealistic, but as you see, as my student is now changing the viewpoint of the 3D view, you can see spikes coming out, which means that if you want to use such a representation for path planning, then these spikes are going to be in your way and you're not going to be able to navigate appropriately. So the big question here is, what is a suitable scene representation? Should I be using a point cloud? Should I be using Gaussian splats that look nice? Or should I be using, for example, voxels that don't look as nice, but they're useful for path planning? So I don't know what the answer to that is. You might think a hierarchical representation is good, or a mixture of many, but that's one big question we are trying to address at the moment. Now, on multi-agent collaboration, imagine that you have now your favorite SLAM system, right, running on board your favorite robot. Let's say SLAM on board a drone, and at some point, this drone needs to forget about the past in order to be able to process what's incoming. And it's constantly optimizing, using discrete time, continuous time, it doesn't matter. It needs to continuously optimize its estimate. And imagine that you have other agents that they all do their own thing, they all run their own SLAM. But before they forget about the past, why not send all this information down to a server or up to a cloud, and then you have this server that can store copies of everybody's estimates about where they think they are and what their environment looks like. So copies of all these maps. Then this central entity could also do some more expensive things like place recognition and optimization, so like bring the two maps together if the two drones have experienced overlap. And then once you optimize, why not inform the participating agents of any changes in their estimates? And this is our first attempt to collaborative SLAM. Basically, it was demonstrating for the first time 3 drones performing monocular SLAM. So all drones here are manually piloted. They run their own thing independently. They know nothing about each other. But they keep sending information down to a laptop. That's the server. That's my student sitting in the sunshine there. The laptop the server is detecting overlaps across different trajectories, and if there's an overlap detected, it brings the maps together, and of course we choreographed the navigation of the drone such that they experience overlap in order to show you that collaboration is possible. So when communication is on, then these drones can collaborate via this central server, and when collaboration is not really on, then they can continue doing their own thing without compromising their own stability. Now, the big bottleneck here, obviously, is the central server. So how many drones can we have, can we handle? What's the scalability of the system, which really pushes us to look towards distributed SLAM problems. And in fact, Mike will be presenting distributed pose graph optimization on Thursday. This is distributed pose graph optimization via contractive belief sharing, and I'm going to call it CBS from now on. And I'm going to go a little bit into the details of it before coming back out. So given a global graph, so here you can see the graphs of 3 different robots. You now see the global graph, but what we're giving to basically the starting point of the system is that we have a per robot local pose graph with odometry factors, and we already know which factors are which poses are loop closing poses, and we want to estimate the robot's trajectories. Each robot we wanted to estimate independently, and their relative transformations. So how do we do that? So of course we're not the first ones to think about this problem, and here are some top competitors. So the first 3 systems are optimization-based systems, and you can see that we have some guaranteed convergence, but they have high cost or low cost and low accuracy or sensitivity to noise. And then on the 4th column we have RobotWeb, which is based on Gaussian belief propagation, which is a very nice idea that has this sharing of beliefs, as I explained before for the trajectory optimization, but now is sharing beliefs in this graph of basically relative pose factors. So it has great potential for scalability, but it's not designed for graphs that are not tree-like. So it's sensitive to loops and noise. So inspired by the power of Gaussian belief propagation, we in CBS we employ similar belief sharing procedure between robots, but within each robot we run an optimizer. So you can choose any off-the-shelf map optimizer within each robot. And also another key thing is that we are damping the belief updates according to the Hellinger distance in order to address problems with convergence that Gaussian belief propagation usually has. So this is the global graph, and this is what each robot sees. Each robot sees its own graph, basically. Okay, let's pick the blue robot, for example, robot I. And let's talk about them. So we are running iterations continuously. So robots share and receive beliefs about loop closing poses. Here's how that pose changed. And when you receive a belief, you basically introduce it in your graph and convert the poses into relative pose factors in your local graph and optimize it. And when you optimize it, then you want to prepare on how you publish these updates to the neighboring robot, right, like the red robot there. So in order to prepare, in this preparation, we are approximating the marginals by ignoring the factors to the sender's anchor that we just fantasized before, in order to avoid double counting as much as possible. And also we are regulating what kind of updates we are sending to the sender that originally sent us this robot, using the Hellinger distance, in order basically to have a really small step size to be able to not miss the convergence basing, which is a problem that happens with Gaussian belief propagation. If you've worked with that, sometimes it's fluctuating between 2 different solutions. So Then we run these optimizations continuously until iterations continuously until the residuals of the poses stabilize, and then there's the anchor sharing stage to align estimates that it's following basically the same process but for anchors. And here you can see some of the results on benchmarking datasets. So we take the benchmarking datasets, divide them up into blocks of 5 to simulate 5 different robots. And you can see that probably you can even distinguish the difference between the pose sharing stage and the anchor sharing stage. So first of all, the robots are optimizing their own shapes of the trajectories, and then the relative transformations snap together when the anchor sharing stage starts coming into play. And some numbers to also show that we do our proper evaluation, and Mike will talk about this on Thursday. But effectively, CBS achieves stable convergence even on loopy and noisy graphs and exhibits great scalability. But of course, it's not yet SLAM, so that's ongoing work to also add the map in the equation and how incremental these graphs can be, and hopefully with a code release soon. So to zoom back out now, these were our challenges, and how far along are we? I think that for high fidelity SLAM, we need to think about multimodal SLAM. Which sensor to trust and when? Can we do that automatically? How can we fuse all this data? What's a good trajectory representation that would allow us to undo corrections that no longer seem relevant? Scene understanding. What is a useful scene representation? Is a point cloud enough, or do we want a photorealistic environment, or do we want this environment to be, this representation to be useful for path planning? So maybe you've seen lots of different works that try to isolate the problem as much as possible to try to address SLAM using one particular representation, but it wouldn't work for, it wouldn't look nice, or it wouldn't perform well for path planning. And then for multi-agent collaboration, what's next is about navigation autonomy, I think, collaboration and coordination, and what information to share between agents, because we know that that's costly, and that's where CBS comes in, is trying to minimize communication as much as possible, but also ensure convergence, and where to look for information. So if you are in a very dynamic scene, I don't know, fire, maybe we shouldn't be looking at the fire, maybe we should be looking at things that we can get information from, and then try and map the very dynamic scene. So these are all my thoughts, and thank you very much for your attention.
Okay, thanks, speaker. We can have several questions. Yeah, please come here to this microphone if you have a question for our speaker.
I'll take the first question. Thanks for the great presentation. I'm curious, in this area, in case of distributed posture optimization, we need to consider communication bandwidth, but I guess this is just offline. So can I get some wisdom about the communication efficiency, distributed system?
Yes. So the numbers that I browsed very quickly by here, they are showing numbers of iterations, not necessarily how big the messages are, but numbers of iterations that we need in order to be able to converge. And the same thing for each algorithm. So in CBS, we really tried to minimize how much you're communicating. But it's true. It really depends on basically how big also these messages are. So you mentioned that it's offline. Still, it's offline because of the definition of the problem, that you get one graph and you need to update it. But I agree with you. So definitely communication is something that needs to be minimized as much as possible. Please, yeah.
Thank you very much for your interesting report.
Could you go closer?
Yes. Could you make some opinion about using modern GT-like approach, for example, end-to-end methods for pose estimation, for mapping. What do you think about the perspective in this case when we need to create a single map, a single big multi-robot map?
So the question is about learning-based SLAM, is that? Yeah.
Modern GT-like method, because this is trend mapping.
Yeah, I think we should throw all we have to the problem and then see what performs best. And I think that handcrafted methods are good for some bits of the pipeline, and learning-based methods are good for some other bits of the pipeline. My feeling is that it's a combination of both that holds the key, but we really need to explore both to the bone to see how we bring them together. Thank you.
Thank you for the talk. It seems that the projector is kind of integral to your system. So how do you estimate the trajectory? Do you use visual keys, do you use GPS, or something completely different?
So we try to remain generic, right? In terms of reducing all the information into a representation that could use LiDAR, could use GPS, and we use them as constraints between poses, these factors between poses, and then that's where the cool idea would be on, if you have a very uncertain sensor, maybe this constraint would not be so tight, but if you have a very certain sensor that you trust very well, then maybe these can move together much more than let them relax.
How do you then find the correspondence?
Yes, so of course, if you're using vision, you're going to use a different front. So we have different algorithms. So work with vision-based SLAM, LiDAR-based SLAM. Yeah, so of course, using the front end that is necessary in each situation. Thanks.
Okay, let's thank our speaker again.
Thank you.
As the postdoc, leading the robotics team. In 2024, he started as a junior professor at the University of Bonn and the Blum Institute. Hermann's research focuses on machine learning for robotic perception and scene understanding, developing models and methods to understand an agent's environment semantically and geometrically. He is known for his public remarks on semantic perception, SLAM, and furniture interaction, as well as for regular workshops that he organizes in robotics and marine conferences. Okay, with that, the stage is yours.
Thank you very much for the kind invitation. So I'm Hermann, and I want to talk a little bit about a different thing than Margarita before, and that is once we have good pose estimation, what else can we do with maps? So kind of what comes beyond reconstruction. I think first of all, if you work a little bit in semantic mapping, there has been, at least to me, somewhat of a shock moment, right? There are suddenly these models that can do all the semantics that previously we needed together from multiple viewpoints, and they do this essentially from single images, right? So there was this really nice work on HOFSG, on like navigating to anything that you type in. There are all these different VLAs that can essentially manipulate whatever they see just from an image, and then there's these things in between, like this really cool work on OK Robot that couples them together. Then you have a mobile manipulator, and it essentially just follows your command, goes to an object can pick it up and so on. So this kind of maybe it first comes as a for me that was like we have to get a little bit again what kind of things do we need to map and what kind of things can we do from single images. And I think at least or what I want to propose today is that maybe our idea from before of what goes into a map and what is kind of a prior that an agent brings with them changes. So I think traditionally what we do in environment-specific information in mapping is like all the 3D geometry that we observe, kind of different objects and their locations, the free space. We already talked about planning like how to traverse a space. This is what we need a map for. And then essentially we can store our path trajectories maybe in that. And then our robots come with some priors that are not environment-specific, like their control, like their general image detectors and so on. And essentially like their ego motion estimation, what kind of sensors they have. Often also local obstacle avoidance. And I think what is shifting a little bit now is now we have these large models that we can bring as priors that also come with this kind of language understanding. You might call it common sense reasoning, I don't know, but it essentially tells us a lot about how humans look at the world. But then on the other hand, if we do mobile manipulation, we are interested environmentally specifically in a lot more information than just geometry. Maybe we want to now do dynamic mapping, but we also maybe need to store past interaction experiences, functional connections in the map, essentially a lot of things that are invisible. And there was this question before on what happens now that we also kind of have good prior models on how geometry looks like. And essentially one of the things that we've been working on is looking at if we have really good feed-forward inference for geometry, maybe from multiple views that we can triangulate, then maybe this is not something we need to map anymore. Maybe this is something we can infer when we need it. And so that's the first thing that I want to talk about. How does SLAM and navigation work if we don't use reconstruction, if our maps don't have that? And then in the second half, I want to talk about how can we map invisible information, things that even VLMs cannot infer from images, but that might be really important to robots. So the first thing that we looked at is like the very classical thing. If I have a method now that like master or something like this that can infer 3D geometry just from images and a couple of them, how can I do a much more sparse mapping approach? So the regular SLAM approach that we all know is we move around in an environment, we take different viewpoints. From these, we can kind of re-identify certain key points and we can triangulate their 3D position. And so this essentially builds a map of our trajectory together with a map of the environment, the reconstruction. Now, there has been something that is actually very old, and we found lots of old literature on it, which was called post-SLAM. And even though you might argue, is it SLAM or not, if you don't really do mapping, well, this is what we found as a reference name. Essentially, what happens is you just estimate your trajectory, and then you have some kind of loop closure edges, and you can just do post-graph optimization or bundle adjustment or something like this. And this is what we do in 2GO or 2Go. So we use kind of models like master to directly infer loop closure constraints from just a pair of images. And that means our entire map is just a trajectory together with some keyframes. And then in order to build constraints for our post-graph optimization, what we can do is we can essentially either do scale-free estimation, like a lot of these feed-forward models don't give you scale, actually. It's important to note. But then we can also, if we have a good metric depth estimation, we can also actually get absolute constraints. And we essentially look at two variants. Interestingly enough, the thing that we found is more stable is not something that uses one single feed-forward model. But actually, we combine a couple of different things, and we still do actually kind of more traditional PNP solving for the relative pose, which in the end turned out to be much more stable. But then what we can do is, this was a very cool experiment. We walked around with our robot through the entire building for an hour. So try to take a SLAM data set that is an hour long. You have to actually think about the logistics of swapping your batteries along the way and stuff like this, because your robot might not really have battery runtime of an hour. But this is a SLAM data set. It covers an entire hour of going around the environment. And then the map that we see is just this trajectory. And wherever there's a marker, there's a keyframe. And sometimes we see these loop closure constraints I think I can use a pointer here. Yeah. Sometimes we see these loop closure constraints here. And if we optimize all of this, we actually end up with something that that gets better pose accuracy than I would say the more classical mapping from OPSM 3 and so on. And we can also see we can use this with different sources of odometry, right? So one thing that we assume here is we still use visual inertial odometry or something like this, something that has an IMU and not just images, and gives you a really good prior on how your robot moves. And then you just optimize whenever you see something new. And you make a loop closure, and yeah, you can optimize essentially your pose graph. And so this kind of map is very lightweight. But then again, the question is, of course, how do you navigate in something that is just a trajectory together with some keyframes? And here, one of the works where we got that to work is from TNet. So essentially what we propose is, instead of doing this classical navigation approach where we build a 3D map and then extract frontiers here in order to explore the environment, we learn how frontiers look like from images. So if you have this view here, what you can easily see is there's two doors, and there's actually something here where there might be going something to the left. So this is a subset of the entire corners that you find in the image. And if you build a large data set on which of these kind of corners actually reflect kind of hidden areas that you can see in the image, then from this I can get this kind of sparse set of frontiers. And the amazing additional thing that you can get is you can now estimate how much free space could I possibly see there. Is this just, this small frontier which looks behind the bed? Or is it a large frontier that goes into a new room or something like that? Because I fuse now here visual information with the geometric information from essentially what goes in here is depth. So from this, I get this sparse set of frontiers. And yeah, this is a little bit how it looks like. We get this inference, and we have colored them here now by the estimated information gain. Just as kind of from our data set, we can, of course, at training time, we know the ground truth environment. We can count how many new voxels can you observe. And then we estimate this from just these single images. And this is how navigation then looks like in these kind of environments. We spawn these frontiers as we detect them, and then we essentially trade off how far these two frontiers are away versus what is the information gain that I estimate for these. And we get to a very efficient exploration policy that actually beats a lot of the geometric approaches while having a much more lightweight map representation. In particular, so we look at two variants. It's still actually useful to keep some kind of occupancy grid, such that you know which kind of free space you visited before. Frontiers you can directly discard. But if you don't want to do that, essentially what you can end up with is just a topological map. It's just that you come to a viewpoint, you see some frontiers, you decide you visit this frontier here, you find a new frontier, you explore that as well. Now you figure out, okay, there's no new frontiers, means there's nothing new to explore. So now I remember I also detected a frontier over here. Without any map now that I need to plan a path, I can always backtrack to from where did I see that frontier. And then we assume if I can see it, then I also find a way visually just from this single image to navigate to that new frontier. And this essentially is a little bit less efficient because sometimes we have to do detours. If we don't know exactly the space in between here, we don't know if we can directly traverse here. So we have to do a little bit of detours. It's a little bit less efficient, but we have a much lightweight map. And then, yeah, this is how this looks like on a single robot. Now, this robot, if you've ever worked with a Spot, it has a really bad depth sensor in the hand. So all of this that you see here is actually just with a metric 3D estimate. So just a kind of estimate of how the real depth would look like. And still it builds kind of a nice map of this entire environment. So we took this one step further now, not just looking at exploration, but looking at navigation in general. And what we find is that FrontierNet just gives us a very general way of prompting VLNs for any kind of other thing that we're looking for. So what we do is we run now FrontierNet on an RGB image, and from this we get these kind of set of mark prompts. So set of mark prompts has been shown to be a bit of a, I think it's always impresses me how well that works. It works in a lot of different cases. You see people using this for manipulation and for other things. Essentially, all you do is you generate an image in which you have, like here now, marked with letters, these different marks in the image. And now I can give this to a VLM to query, I am looking for a fridge. Which of these leads should I best go to? So all that we get out is kind of a ranking. And all of this reasoning here can happen entirely in image space. All the problems that we have with VLMs not having really good spatial understanding or something like this, we get around, because all we need to decide is just a decision between these points on the image plane. And we know, of course, their 3D correspondence from our estimated frontiers. So with this, we can do, again, navigation, but now we can actually search, for example, for objects. So we don't do a general exploration of the environment, but we always weight these frontiers based on how likely is it that I find a certain object there. And we see here how the robot explores the environment, looks around. Every one of the keyframes that we gather along the way, we run a detector whether we found the object. Now we see here, actually we found the fire extinguisher, and then we just approach it. And so this we can do in kind of classical object goal navigation, but you will also see some examples in our paper that then look at more general things like find a way out of this room or something like this. And just as a teaser, as the next step, even on top of that, what we're looking at right now, and these are some experiments from 2 weeks ago, is thinking about next best view as a general kind of way of learning to move around. So if we have a lot of these visual policies now for manipulation, which can, for example, pick up a mark or something like this once they see it, then navigation essentially is the problem of getting the camera somewhere or moving the robot around in the environment until it's close enough that it can run a local policy to manipulate something. And so this is what we're looking at here, essentially trying from many, many videos and language annotations of these, trying to figure out how do I need to move around in an environment? What is the next best view given a certain query, such as what is left of the oven or what is on the table surface or something like this? And then we get to, I hope the video plays, yeah. Then we get to something like this here. So we can chain just very simple commands, such as see what is on the table. And we get a next keyframe. Now we can detect an object in here, and we can run something else to just take the red mark. So my takeaways from this is that, first of all, I think good interfaces are really important. It's not that you necessarily need to, or at least I'm not a fan of directly end-to-end learning like navigation or something like this. But in the end, just a single interface of an image with like a nice set of prompts is actually really powerful and beats a lot of these vision language navigation networks and so on. On the other hand, I want to kind of spark your imagination, as we saw that for lots of tasks that we thought we require really dense mapping, we don't necessarily need it. There are other ways, and you end up with much more lightweight and scalable maps. But of course, none of this is really possible without robust autonomy. So if you're on a robot that is a drone that flies really fast, you still, I think, first need to figure out exactly how you move around. All of this that we do here is very slow robots walking around, and they have really good state estimation, but this is what you can then do on top. Okay, so the next part is a little bit on, once we have like very sparse maps, maybe what is other information that we require in our maps that is maybe not visible from single images, but is really environment specific, and we want to store it in an environment specific kind of data storage. And here, a lot of the work that my students and I have been doing follows this general concept of scene graphs, or 3D scene graphs that I think many of you are familiar by now. We can think about them as hierarchical graphs structured on different layers that give us different levels of abstractions. So we can have very geometric detail per object, but we might also just have a single node that summarizes an object, or we can cluster objects together into like all objects in a furniture, and then all furniture in a room, and things like this. And we end up with a very sparse structure dependent on how deep we go in the scene graph. And then you see an example of how this looks like in the lab on the right. And these scene graphs have been very nice to essentially build mobile manipulation systems. Right, so you can do something like bring me the water bottle, and essentially what comes out is we just have to search in our scene graph for the one object that satisfies this query, and now we can take the geometry, we can plan a path, and we can pick up the object. And all of this works because we have just a kind of object-centric representation from which we need to pick the correct one. And then, by the way, the navigation here is just really local navigation with the obstacle avoidance, which is why you see the robot here kicks a little bit the table. Okay, so the next thing that we can do with scene graphs and why scene graphs are really cool is because we can easily update them as dynamic representations, right? So here you see Tiag, our student, kind of picking up this object and can easily track it. And these kind of interactions, because we can map them, we can also replay them with a different embodiment. So just maybe to look at this one more time. Since every node now is kind of its own entity, updating its position is very simple. So as long as we can track how it moves around, we can easily build these kind of dynamic representations of the environment. And because, essentially we can couple them with different single manipulation policies, then we can essentially chain a lot of things together. However, a nice additional property of scene graphs is because they are very sparse, we don't necessarily always have to map all the dynamics in an environment. So this is a work in which we found that if you just take the kind of abstract layers of scene graphs, you can actually sparsify this very easily in just a topological JSON. And these are then small enough that you can give them even to local LLMs that you can run kind of on your classical workstation. And interestingly enough, because now you have a really good semantic prior, you can find objects with this that are dynamic or that are not even like present in the mapping session at all. So imagine you run once a mapping session, now you want to find an object which was not even present or has been moved. Because we have semantic priors of where they might be, we can very easily decide, okay, this is a good room to look for this general object. And we're much faster than kind of a more classical semantic mapping approach that would just try to remember where every object was and go to the last known location and from there just explore. And if you want to know more about this, Fujing is presenting this as a poster tomorrow in the afternoon. Now, this is just about objects. I think the really cool thing that we can do now on top is map things that are really invisible. Such as this problem of we have two light switches and two lights, and we want to know which light switch operates which lamp. So obviously this is something we can find out with a robot through interaction, but it's not something that any VLM can tell you just from a single image. However, if we have something like a map, which is environment-specific information, then after kind of trying this out, we can very easily make these connections in a scene graph as functional connections, and the next time we want to turn on a specific light, we don't have to try them all again anymore. So this is, I think, really the purpose of a map. Is to store these kind of information. And so this here is then essentially an exhaustive way of doing that. However, in a follow-up now, we couple this with a very lightweight factor graph optimization, because often enough you have certain priors. You have certain priors such as one light switch operates one light and not kind of, two different lights is less likely. Similar as for oven knobs and so on. So we can put certain priors on what we think is the most likely connection. And once we find out that one light switch operates a certain light, then all the other light switches are less likely to operate that or something like this. We can be a bit more smart about how we explore the space and more efficient. And Kaishan is actually presenting a poster in this workshop this afternoon if you want to know more about it. So I will move on to the last thing. And this is something where I don't have a solution yet, but I'm very kind of curious, and we want to put this out there such that you can try it out as well. And that is mapping physical properties. So now that as we move towards robots that interact more with their environment, there's a lot of other invisible information that is super relevant to map and kind of keep track of. One example is the forces that you need in order to operate something, or essentially just the articulation parameters of different doors, whether it opens to the left or the right, whether it's something that you pull out or that kind of rotates downwards. And this is a new data set that has just been online now for a week that we call HOI. And it's on force-grounded articulation interaction. So essentially what you see here is we went to a furniture store, and I'm not sure if I can tell you which one, but you might be able to gather it from the images that we store. And we operate essentially, I think, 300 or 400 different doors and drawers. And you will find that, then essentially we have these kind of gripper on a stick setups in which we have force torque sensors. So we can measure the interaction force for every one of these demonstrations. And if we project this, for example, along the articulation axis or something like this, we can see something like this here. So we have this like very, very normal wooden drawer. Then we have something that is actually with a magnet. So you need to have a little bit more force to open it. Then we have this fridge where you have to kind of overcome the force of the vacuum, and this oven door. And there's kind of two interesting things to that. First of all, they do have different properties of force interaction that you need to know about, and that is maybe useful the next time you want to interact with that object. The second thing is it's actually really hard to kind of model it just explicitly. So we find for a lot of these, the force that we apply is very dependent on the articulation state. You have often these kind of break-even point for an oven that stands open with like 30 degrees, and then you need to have force again to pull it further down and so on. So there's lots of interesting aspects as to coming up with a way how to map this efficiently. And just to give you an overview, so we've recorded all these interactions with both exocentric and egocentric viewpoints and with different types of manipulators. So there's human hands, there's our custom gripper with force torque sensors, and there's the UMI gripper, which is maybe more classical for these kind of parallel fingers. We have tactile sensors there, we have force torque sensors. So essentially you have a lot of ground truth. And now we want to find out how can we build efficient scene representations that map these kind of hidden states of the environment. Okay, so to wrap it up a little bit, I talked about that kind of the priors that we bring now on robots that maybe we didn't have access to before, and how that can change what kind of information we need to actually store and reconstruct of an environment, and what kind of information we can essentially infer on the fly. And specifically because we can kind of make some space here by maybe not having to reconstruct the explicit 3D geometry, then we open up space for a lot of other interesting information that interactive robots such as mobile manipulators need of the environment. Okay, with this, I want to thank all the students and collaborators from ETH and University of Bonn who worked on these projects. And as I said, there's some posters that you can check out in the afternoon and tomorrow. And now I'm happy to take questions. Thank you.
Well, we can have questions. If you have from here for this microphone.
One of your key takeaways was that having good interfaces is better than having end-to-end learning. So to kind of relate the questions, one is what makes for a good interface, and the other one is this a matter it just makes engineering easier, or is it kind of a higher kind of principle that you think decisions in principle better? It's not just that for.
That's a great question. And I think actually to both questions, I have the same answer. At least in my opinion, what makes a good interface is something such that we can connect interfaces with either very good algorithms or very good data. So that's why, for example, I think images are a great interface for semantics, because we have a huge corpus of images that have annotations and relations to language. Whereas for 3D, as we all know, that is not the case, right? It's not that we have like an Instagram full of 3D scans or something like this. It's much smaller in scale, and therefore our kind of 3D semantics to do this directly is much harder to learn because we have less data available. So maybe images are a good interface for kind of language and semantics. Yet then, if you want to navigate, of course, something like poses are really great interfaces, right? From poses, regardless of my embodiment, I have really good methods that can plan a path. or like poses or waypoints or something like this. So yeah, I hope that answers both of your questions.
I have also a big question. Thank you for your presentation. When you talked about mapless navigation, mapless approach for for navigation, you demonstrate for visualization map. And what about future perspective of mapless approach? Because for visualization, for explanation, you still are using map, 3D map.
That's, yeah, at least partially correct. So here, for example, this is not really a map. We just have this kind of 3D scan of the environment from some other data set, and we just render our map, which is just this trajectory in there, right? So you can, if you have something else like a floor plan or something like this, just to visualize something, you don't necessarily need this reconstruction. But I think the other point is we can always run reconstruction. Like that's the whole point. We don't have to run it on the fly. We don't necessarily need it all the time on the robot because maybe we can do navigation without. But if I want a reconstruction, of course, I can always take my 10, my 20 keyframes and run them through something like Map Anything, and I get a nice reconstruction out of it, right? Or I can maybe run them through a feed-forward Gaussian splatting if I want to have really good renderings or something like this. So we all know that we need different map representations for different tasks. So instead of reconstructing a specific one during SLAM, we can generate any kind that we need on the fly.
What about safety of such mapless approach? Because it's maybe dangerous because we can't explain what they're doing in this end-to-end approach. For example, when end-to-end model working, it's maybe a problem for safety.
So let me think how you refer to this question. I think, okay, so I think here's a big difference between kind of triangulation methods that now just work from multiple views. They still have this physical grounding, right? We can still put poses in that we have as input, and we can just get a good reconstruction. Or something that infers everything from a single view. Of course, if you just have like monocular depth estimation, that is maybe less trustworthy. But I think here you always have multiple viewpoints, right? Whatever you want to create, you always already have poses of your keyframes, and you can run something that is actually physically grounded.
Yeah.
We will have the last quick question.
So I think your research is mostly focused on the images and without using map representation, but how it scales to multiple sessions or over long horizon tasks that should be run over and over.
Yes, great. So for example, for this 2GO SLAM thing, this is one of the key advantages that it runs over long horizons. As I said, like we run this on like an hour, and most of kind of bundle adjustment based approaches, they are not real time anymore. Their computational complexity grows with the map. So we run this also on a data set VBR from Rome, which is also very large scale. And again, we kind of show like this is one of the few things that can make this in real time. For multi-session, this is something we're actively working on, but I don't have an answer yet.
Thanks so much.
Let's thank our speaker again.
Thank you.
Okay. And then we can share. There we go. Yeah, great. Okay, thank you. Okay. All right, so let's get started. Today, I want to talk about deep networks and just sort of what sort of supervision we've been using so far across the past, say, 10 years or so. And just to kind of give a quick overview of the landscape here, we've been looking at deep neural networks as these highly parameterized functions. And of course, because of how many parameters they have, they tend to require a lot of training data. And because of this, the easiest thing we can do is to collect them, right? And we've seen how this may amount to thousands of hours of manual labor. And one of these data sets is very seminal. It's called ImageNet, where we've collected images of dogs, cats, sailboats, and we've attached labels to them. And if you were to train a classifier with this, it's generally pretty well generalizable. Now, we've seen that, as it turns out, if you were to scale up the supervision, the performance also scales. So one solution is, why not just label more data? But this occurs, of course, thousands of hours of manual labor, and there's been a lot of efforts in the vision community to sort of develop these automated data pipelines. And the outcome of this is to generate a large data set that you can now train one of these generalizable models. Hopefully, you can adapt them and transfer them to other tasks, and they would give you wonderful results. And of course, one of these data pipelines involve a number of filtering, maybe deduplication, quality assurance, and steps of these sorts really involve retrieving data samples that are similar to what we have curated existing data sets. And of course, this is to make sure that whatever supervision that we generate is of high quality. The outcome of this effort here is 142 million images that are used to then train a downstream neural network that's quite generalizable. For those who may be wondering, this is called Dino. And we've seen something very similar in the case of depth estimation or 3D reconstruction in general, where a collection of these curated data sets of images and 2.5D range or depth maps are now assembled together to train depth estimators. And this model can be seen as a part of a greater pipeline of sorts to infer depth, generate pseudo labels, and now you have a wealth of data which you can then retrain a depth estimator from this. The outcome of this effort is 63 million examples of pseudo-label depth maps. And this process, of course, can be repeated with different seed models, different pre-trained backbones, different even multiple seed models. And this work right here is something called depth anything. Now I want to juxtapose these two processes side by side, so sort of two different visual tasks, and just try to draw a general trend. And what has emerged is a school of thought that involves collecting large volumes of training data, annotating them through these data pipelines, and then training or retraining new models and stuff on the resulting large-scale data set on some GPU cluster. For those who are wondering, there's a very fancy name that's attached to these things. They're called foundational models. And the outcome of training such on these large volumes and such is that there's these high fidelity outputs that can be generated. And these models then generalize across environments, 3D scenes, and you'll have recognized some of these figures from the recent VGGT map of anything, maybe Pi 3. Now, I want to sort of give you both sides of the story. So this is the happy side, where you get nice point clouds, whether it's from a single image, from a sequence of images, or from maybe even from indoor, outdoor, aerial, all of such. But here are also some of the not so successful 3D reconstructions where straight roads are now predicted as curves, points and objects are now distorted and incongruent, and despite being trained on tens of thousands, hundreds of thousands to millions of images, these foundation models still output these erroneous cases. And this happens when you transfer them to novel environments, deploy them on different sensor platforms, and their errors really stem from the large-scale data curation pipeline that made them possible in the first place. And this is because machine learning says something very fundamental. It says that given that I have some learning algorithm, what I expect my training data to be is to be representative of those at testing. So this means that the mere act of collecting these large-scale data sets has already imposed what you would expect to see during test time. And so then this becomes a different problem that we're dealing with. The problem of guessing what we're going to see in the future. And of course, the methodology that we can try to go for is to just aim to collect as diverse as much as possible of these unknown data samples, right? To make these educated guesses of what we will see at test time. But it's really hard. And so that's why you get some edge cases here. But now let's fast forward to test time cases, and somebody has given you data, right? It's a very painstaking process to collect data. If someone's giving you data and you've made a mistake, can we do something about the model at this case? Maybe to adjust its parameters, to adjust its inference. And so today what I want to do is to present an alternate view and consider how one can enable these models to adapt to observations at test time without human intervention, and further to continue to learn in a lifelong continual learning fashion so that we can extend ourselves beyond just simple 3D scenes, perhaps even to additional sensors. And to take a step forward in that direction, we have designed unsupervised methods to train these deep neural networks, to take in images, sparse range, inertial data to infer the dense depth of 3D scene. And of course, the fundamental idea behind this, many of you guys may have already know about this, is that we want to validate the compatibility between what we've estimated and the multisensory observations. And this will be a general learning principle that you may have seen in the so-called self-supervised learning, neural radiance fields, Gaussian splatting, SLAM in general. And the process really is to check whether or not the estimated 3D scene can generate the observations through what we call reconstruction or recreation of the sparse point clouds or images from other views of the same scene. And then we will measure their error, and we can concoct some loss functions out of this. And this is essentially going to manifest in this form. And the first term there, the first equation there is assuming that we're processing data causally is a photometric reconstruction term where we measure the color intensity differences between an observed image at some time t and its reconstruction at some time tau. The second one there is a sparse range reconstruction term that penalizes the deviations of the estimated depth from the point cloud that's been projected onto the image plane. And of course, you can imagine that this will work for cases of using VIO, SLAM-based systems. If you had some range sensors such as LiDARs or radar and stuff, you can also apply these cases. And this entire process actually can be integrated into any form of autonomous systems relatively easily. And if you were to do all of these things that I've talked about, then minimizing an objective this form allows a model to continuously learn and adapt to novel settings for both indoor and outdoor scenarios, and virtually exploit the virtually infinite amount of training data that's observed simply by navigating through the environments. So here's an example where we deployed our model that was trained on some classrooms, gardens and such into a household study room. And on the left there, what you see is the observed image and the ground truth. And on the right is the output and the error measured over time. And you'll see that in the initial 20 frames or so right there, the error is actually quite high. It sits at about 180 millimeters. And over time, it decreases to around 30 millimeters. And that's because it's never seen fancy cabinets, mahogany cabinets, or these nice couches. But it's able to see these images and adapt to it on the fly. So it sounds like that we've met our goal, right? Problem solved. But training these neural networks is actually extremely difficult. And that's because despite what we see as so-called dense supervision, as in that there is a loss being computed at every single pixel, in which case we can see how maybe that there's a lot of constraints being applied. But it turns out that from the visual standpoint, the supervision that you get is actually quite sparse. And that's because the number of pixels that can be uniquely determined is in fact limited to the small areas that are visually exciting, co-visible between images. So anywhere that is homogeneous, anywhere that that may have occlusions or perhaps the aperture problem are not going to allow you to establish correspondence at all. So training these neural networks are very tough. And if we look at these examples right here, on the right is a set of images that we've just taken in their lab. And we're given the synchronized point clouds projected onto the image plane as 2.5D range maps. On the left there again is our training objectives. And we can see that just from this, the photometric reconstruction term only constrains the solutions anywhere that is that's visually exciting, that there are some nice textures and such. Everywhere else that's empty can be constrained by the sparse point reconstruction term, but everywhere else that doesn't satisfy these two constraints have to be handled by some regularizer. In which case, my lab has done some work, but we'll save that for a different topic. This is kind of tough because as you enter into the typical training pipelines, the first step that we choose to take is to augment our data. And when we augment these images, the first thing that we do perhaps is to apply some photometric augmentations, some geometric augmentations. So rotate, resize, downsample. And after applying all of these things, it turns out that the regions that were previously exciting and the points that were somewhat dense have now been downscaled and the homogeneous regions take over. They've been saturated. So this means that we have lost our supervision signal. And so imagine doing this for all your images and such. It turns out that we're shooting ourselves in the foot as we augment our data sets. So then this is somewhat problematic for us because in machine learning, this is the first step that we take. In fact, the side effects that we see here are desirable for many of the visual tasks that we care about, such as detection, segmentation, the saturation of colors, the losses in details. The interpolation artifacts are nuisance variables that we want to be invariants to. But now, as we move towards these large-scale pipelines and such, the more we augment, the more we degrade our supervision signal. So it's not too surprising that in most of these conventional pipelines and stuff, we rarely apply large-scale augmentations to training these unsupervised depth estimators. Now, the tricky part is that we need them because if you don't augment your data, then your model's not going to generalize. It's not going to be robust to illumination changes, different colors of objects, different orientations of your camera. And so you can imagine that geometric augmentations can simulate different camera parameters, small baseline translations, maybe some in-plane rotation. And without any of these augmentations, we're actually going to end up with something that doesn't work at all. But on the other hand, if we have them, then we can't train. So we're at sort of an impasse here. And so we thought about what sort of things we can deal with these cases. And during a lecture I guess it's lecture 2 of computer vision, we talked about something called group transformations. We realized that there are some very specific properties that enables invertibility between some of these transformations. And so one can imagine that if the augmentation that we choose are follow these transformation groups, then perhaps we can invert them. And if we do, then we can get back the supervision signal that we had before. And so this is precisely what we do. This is a very straightforward idea where we said, let's not compute the loss on these augmented images and stuff, but instead simply compute the loss on the original inputs, but perform the inverse transformation on the outputs to get back to the original input space. And so if you were to perform these operations and such, then you actually be able to handle the sort of misalignment in the output space. And this process here is called aug-undo, where we literally undo all of the augmentations by applying the inverse transformations to our examples. So the first step is that we augment the images, both whatever that you want, color, geometric, and such, perform the feed-forward task, and now we undo these augmentations to move ourselves back. And turns out that if you were to do this, you can now apply any augmentations that you may choose as long as it follows this group structure. And so this process is called aug-undo. It enables a range of previously infeasible photometric and geometric augmentations so that you can perform this learning of unsupervised step more scalably. And it can be applied in a plug-and-play manner to any of the existing monocular depth estimators, monocular depth completion networks. The difference of them is very small, only the change in inputs. And to test our approach, we tried this on a couple of different data sets and found out there's a big boost in performance, whether it is for the in-domain cases or perhaps even generalization. And so if we think about what these augmentations really are doing, they are actually simulating some of these edge cases that we may see maybe in different cameras, in the different orientations, maybe small baseline translations of the camera, and having these transformations as part of the augmentation pipeline helps us generalize quite well. Now, the tricky part is that because we've limited ourselves only to these simple uniform changes in the image, that we're applying brightness changes, some color changes, some small baseline rotations, translations and such. We actually don't model the predominant case of what we call covariance shifts in the data. And so some of these nuisances that we typically encounter in real world cases, they're much harder to handle. And imagine yourself driving out at night, some illumination is low, there's specular surfaces, maybe there's some splatter of rain, maybe sometimes there's fog. We're in New Haven and stuff, so every time it gets rainy and stuff, there's always fog around. And even for me, this is very hard to deal with. Now, if you take the conventional case of these large-scale pre-trained model, the solution is quite straightforward. Collect the data, bring it back to our data pipeline, relabel, retrain V2 or V2.1, V2.2, and you're ready to go, right? But we have to trust that our data pipeline is going to produce good pseudo labels for these things in the first place. But we know that learning really is compression. So if you had compressions, the previous knowledge into the model before, and it can't do well on the current sets, chances are that you'll still encounter some errors and such, especially with supervision signal when you transfer them to these hard cases. But perhaps we can perhaps we can figure out some ways to transform these things at test time, or transform our predictions at test time, so that they're more conducive towards these difficult scenes. And the way that we've kind of looked at it is quite classical. We were thinking about something called energy minimization, which is something that we studied during my PhD. And so energy is a quantity that we can use to quantify how well aligned a particular data point is with respect to some distribution. In this case, we care about the training distribution because we've trained well. We know that we can generate some high quality predictions from there. If there is a way to tell whether or not we're experiencing these L distribution cases, perhaps by minimizing this energy quantity, we can bring ourselves from this L distribution state back to these high quality estimates. And so to do this, we take this energy-based approach where we try to quantify how far some of these predictions are from what we deem as in distribution. And we're going to take a minimization approach at test time to sort of reduce the energy and bring ourselves back to these high fidelity estimates. But the tricky part is that when you need to determine the energy model in this case, you need some data points that are considered high energy and some that are low energy. High energy means that they're out of distribution. Low energy means that they're within distribution. It's very easy to get within distribution cases because that is just a training set. How do we get the out of distribution cases without making assumptions about what we observe in test time? Well, we drew some inspiration, something called adversarial perturbations. These are small, imperceptible signals that you can add to images where they cause catastrophically big failures in the outputs for some of our deep neural networks. So you can craft these specifically for different networks and such, and add them onto the inputs, and you'll simulate these OOD cases. And if you were to do this at scale, it turns out that this is actually exploration of a data space. Every single time you add a perturbation, you generate new data points, in which case, if you were to do this at scale, you would populate the entire data space with some of these OOD examples, and you will be able to find a nice decision boundary transitioning from OOD cases to your in-distribution cases. And so you can take these examples and train an energy model with it. And once you've done this, you can now perform energy minimization on the fly at test time. And by reducing the amount of energy within the system, you'll be able to get nicer reconstructions within just one single step with a small tweak of the network weights. And so these are particularly useful for real-time systems. So you will now be able to adapt on the fly to this energy minimization process. But for those who have worked on energy minimization, you know that you can take iterative multiple steps and such. So this is precisely what we did for medical images, where there's no constraints on the amount of time you can spend optimizing at test time. So we demonstrated these things for medical images, where if you were given an erroneous initial prediction over there, and you can quantify its estimated energy on the right here, by performing this minimization process, you'd be able to recover a nicer in this case, a myocardium for your predictions. And so this sports some level of explainability, interpretability, which doctors really like. And if you were to apply this on different patients and stuff, turns out that you can actually personalize your model towards every single patient. But of course, as we adapt, we end up forgetting. And this is the classical case of catastrophic forgetting in machine learning. So your model can get good at something, but it will forget everything else. But then as you adapt and stuff, this model actually collapses. And so you end up getting meaningless predictions after adapting for several steps. And so then what we end up doing is that we take on a problem of continual learning to extend these models across 3D scenes. One particular branch of ideas came from psychology and cognitive science. There is somebody named Eleanor Roche. Back in the 1970s, she developed some theories called prototypes, and this would be able to allow us to quantify how we can characterize different scenes. And so our methodology here is very simple. We would freeze a model and use prototypes to describe new incoming scenes so you can adapt to them as specific experts. And if you were to do something like this, you would get a nice phenomena where we see how each prototypes are the stars here, being able to model different 3D scenes and environments and stuff. And so you can extend a model from one that's trained on a very specific set of data sets to new ones over time. And one might imagine that this same process can allow you to extend to new sensors. And so we will skip ahead to this set of slides here, where in fact we saw the examples we saw earlier, where foundation models are unable to make high-fidelity estimates on fisheye cameras. And so if you were to take this sort of this prototype approach, continual learning approach, you would be able to extend your foundation models to different types of cameras, even to new sensors. And so I just want to show a few examples of such results that we've had in this case, where previously you had foundation models such as UniDepth V2 map anything that failed on fisheye images or panoramic images. And by performing this sort of continual learning on them, you would now be able to extend them to all of these new cameras, and with zero catastrophic forgetting, as in you're completely backwards compatible. So you'd be able to do everything that you wished for previously, but place them onto a new camera system, and they will work seamlessly. And if you were to follow this line of thinking and such, you can in fact add them to tactile sensors, audio sensors, and so on and so forth. So in fact, the future that we foresee in multimodal models is not just vision language. For those in vision and such, we've always been multimodal. We've never stuck with just images and such. But I think there's a very clear path in how we can turn our multimodal models to something that's generalizable across different sensing systems or sensing platforms. And so I want to end with a few remarks. Some of the things that we want to highlight is really in how we can adapt or how we can handle these edge cases. The way that we've done so is really by this online test time adaptation process, which we've done some work in. So we want instantaneous adaptations that happens within milliseconds of the model seeing new data points. But as the model begins to adapt, they also forget. So we want to deal with continual learning or these model extension methods, allowing us to extend beyond 3D scenes, perhaps new sensor modalities, so that we can place ourselves in platforms that we have never seen before. Perhaps if you were to see the intersection of these two lines of work, you'll see that we're heading towards what we call test time continual learning, where we can continue to learn, get our models to gain more and more knowledge over time and never degrade And this gets closer to how humans operate. One particular topic that I didn't touch on is something called uncertainty quantification. I think this is probably the most overlooked topic in computer vision today, and perhaps where this uncertainty may stem from, either from the data or maybe from the lack of knowledge in the model. And looking forward and stuff, perhaps we can even have active continual test time learning models and stuff on the horizon. So with that, I'll wrap up and thank my collaborators and such. Thank you very much.
Alex, we can have one quick question. If you can make it. Come to the microphone. Okay, I have a quick question for you. Like, for the first time of application, if you return or you continue learning of the application model, maybe you forget if you retrain them, then you forget something. How do you evaluate?
No, that's a great question. So once your waist drifts, there's no going back. So that's why we need to that's why we decide to freeze the model weights. So you have what we call maximum stability, as in that you retain everything that you've learned before, and you want to encourage some plasticity or some degrees of room to adapt and stuff. So we've actually deployed an extra small sets of weights, some of them that are relatively lightweight, so that we can adapt to new scenes. And so this gives you that nice trade-off between the two.
Great. Again.
Thank you very much.
Okay, this concludes this multitasking.
Good. All right. Sorry about that. Okay, well, thank you very much to the organizers for the invitation to join the workshop and to speak about, give some thoughts about multimodal. We all know that we can now write a paper about a data set. Turns out you can write a paper for IJRR about a data set, and wearing my TFR hat, you can also now write a paper for TFR about a data set. So I figured if you can write a paper about a data set, you can also give a talk about some data sets. So I'm going to use this talk to advertise 3 new multimodal data sets from a variety of different domains that we've been working on and that we've made publicly available in my group. So, a little riff on the Wizard of Oz, roads, forests, and lakes, oh my, new multimodal data sets, and some thoughts. So the agenda is pretty simple. I'm really just going to talk about these 3 different data sets. One on the road with an expansion to the Boreas data set that we put out a few years ago. One off the road with the FOMO dataset, and then one on the water with something we're calling the Canoe dataset. And I'll get into the details of each one. So let's start with the Boreas dataset. So a couple of years ago, my group put out this new on-road driving dataset called Boreas. And what we really wanted to focus on in Canada, we have slightly different weather than in California and in Texas and Phoenix, where a lot of the autonomous vehicles are being tested. And actually, Steve Waslander is sitting right there. We have a big program of research centered around trying to get self-driving cars to work in snowy winter conditions in Canada. And as part of that, we put out this Boreas data set. So we drove around on the same route for about a year. And we tried to gather data with radar, LiDAR, and cameras across all of these different conditions that you might experience in a year of driving in Toronto. Toronto is actually not particularly representative of how cold it can get in Canada, but nevertheless, that's what we have. And we put this data set out. It's hosted on AWS. There's a leaderboard, all that stuff. It's getting quite a lot of traction over the last couple of years. So I encourage you to check that out. But what I wanted to talk about today is an expansion pack, if you will, for the Boreas data set that we're calling Boreas Road Trip. So we went back out on the road again, but rather than repeating the same route that we'd done in the original data set, we're now trying to really produce some conditions that will make all of our algorithms break. And we sought out the conditions that we thought would be the most challenging. So we do have some new suburban data sets, some highway stuff, but we've also headed off into some things like geometrically degenerate situations. So we found the longest tunnel that was near Toronto when we drove the car through that tunnel. That turns out to be pretty challenging for a lot of our odometry and localization and mapping methods to be able to handle that. We also headed off into some forests with rolling and pitching roads and not a lot of man-made infrastructure. where the leaves and things will change over seasons. We headed down some farmers' roads, and we deliberately drove a car in front of our data collect car to make a whole bunch of dust come up off the road to kind of make our sensors be occluded. And there's lots of nice details with this expansion pack. It's available right now online. You can check out the QR code. So let me tell you a little bit more about it in detail. So as I said, we have these structured environments. We are gathering data across all the standard sensing modalities. Maybe radar is not so standard, but we have this imaging radar on there as well that we're gathering and producing that data. So structured data sets, all of the different loops are documented there. It's highways, and that includes going in these tunnels, which I think take your favorite LiDAR odometry algorithm and try and run it on these tunnel environments. It will probably break unless you've got something clever going on there. And then these rural environments that I mentioned. So lots of different things. I talked a little bit about the sensors that are there, bit of an eye chart, but these are the specs of all the sensors. I will mention and call out particularly that there are two different kinds of LiDARs on here. So we have a standard Velodyne Alpha Prime, 128 beam, but we also have one of these EVA Doppler LiDARs. How many people have heard of Doppler LiDAR? Right, in the multimodal session, only 10 out of 100 people have heard of Doppler LiDAR. So this is now using frequency modulated continuous wave ranging rather than time of flight. And it works basically like a radar so that you can get both range and range rate on every single point in your point cloud. So that becomes interesting, right? Now you have a velocity channel in your LiDAR that you can use to solve some of these geometrically degenerate problems, for example. So we've done a bunch of work on that. I won't talk about the research, but I'm trying to put these challenges out there for you to think about, and maybe you can take this data and come up with some new algorithms to solve them. I'd like to think we've done a pretty good job on all of the calibration and all of that stuff. So everything has been carefully calibrated. All the transforms are there. Everything's been time synchronized and validated. So hopefully you won't have a lot of issues. The ground truth is all generated through separate sensing from all the sensors that are in the data set. So one of our partners is Planix, which is one of the world leading providers of GNSS-INS systems, GNSS-INS systems. They actually do all the post-processing of the ground truth for us because they're much better at it than us. So everything should be reasonably good down to about like 3 centimeters on the road. And if you want to know what's unique about this data set, we can sort of benchmark it against a couple of other data sets that are out there, starting with Kitty and all the way down to, you know, our old Boreas data set and the Oxford Robot Radar data set. And if you look at it, really, there aren't too many data sets that have radar and have been across all of these challenging different environments provided in a single framework. So we like to think it's offering something unique to the community. So here, again, are some sample data from all of these different environments. You can see the radar data across the bottom. And for anyone who hasn't worked with radar, take a look at the video under the tunnel column, right? So you should just have 2 clean walls, but you can see that you get all of this interesting ringing. It's such a clean, perfect, geometrically clean environment that you can actually see the ringing of the radar because it's sort of bouncing between the walls and coming back to the detector. So there's a lot of artifacts with radar, lots of things to work on still to make this type of data useful. I won't bore you with the numbers. We run lots of baselines on the data to make sure that everything, you know, actually is usable and works, and what doesn't work. So we've definitely found lots of situations where the standard algorithms you might download don't work very well on this data. So I encourage you to check it out. There's about 650 something kilometers of new data that's all curated there for you guys to play with. This was a fun image. So as I said, we do have some snow in Canada. And even in Toronto, we had a fairly snowy winter the year that we gathered this. And you can actually see in the LiDAR point cloud, there's a geometric change in the environment just from the snow piles that have accumulated between summer and winter. And that actually does mess up some localization algorithms, believe it or not. You can, you know, imagine what might happen if you built a map with one and then tried to localize with the other. So things to think about. There's a development kit, there's a leaderboard. Everything should be ready for you guys to use. Okay, so that's the Boreas RT expansion pack. Now I'm going to turn to the FOMO dataset. And actually, we have the leading force behind the FOMO dataset in the audience. Matej Boxen is right there. Raise your hand. You can talk to him about the FOMO dataset. All complaints should go to him. All praise should come to me. So this is a really cool data set. Now we're getting off the road into a forest environment. And I should say this is mostly the work of the University of Laval and NORLab in particular. So that's Francois Parmelot's lab, but my lab had a little bit of a role in this, so I'm going to talk about it. So here's a view of what you might expect to find in the FOMO dataset. We're gathering data on an off-road clear path warthog UGV across all seasons for a year. So kind of like the Boreas one, but now in an off-road environment. So these are forest roads. There's so much snow in the winter that it's actually pretty hard to get off the road and actually cover all 4 seasons. So we've mostly stuck to the forest roads here. But they do roll and pitch quite a bit. So you're going to experience quite a lot of 3-dimensional motion in these data. And where might this be applicable? There's a lot of work to think about how to automate, for example, these trucks in a forestry operation. There's some machines that cut down the trees. Then there are the trucks that haul them out of the forest onto the main roads. And those sometimes have to go hundreds of kilometers out of the forest. And it's actually very hard to find drivers to drive those trucks. So there's a lot of different people looking at ways of automating those long haul forest trucks. And so maybe this data set would be useful for building localization and mapping for that, for example. And this image is a great representative thing of what a forest road could actually look like in the summer. That's a road. We're looking at a picture of a road right there. So think about that, right? How are you going to get your perception system to be able to look at that and say, yep, that's a road that I can drive on? The location where we gather this data, so FOMO doesn't stand for fear of missing out. It stands for the Forêt Montmorency, which is the largest test forest in the world, research forest in the world. There's a lot of ecology studies and things that happen there, but Francois' lab has figured out how to get in there and operate, and it's a really amazing place to go and do some field trials. It will very quickly humble your algorithms as soon as you try to run them there. It's a very challenging environment. So again, as I said, 4 seasons, there's 6 different main trajectories, which are the different colors in the top left image, and about 64 kilometers of data. And if you're wondering where this is, if you know where Toronto is, it's northeast of Toronto by a few hundred or several hundred kilometers. What's unique about the FOMO dataset? This is a cool image that Matej put together that tries to put a lot of other data sets in context across these different axes of repeated traversals on one side, multi-season and off-road. And I guess we kind of sit squarely in the middle or triangularly in the middle of those things. Whereas some of the other data sets maybe emphasize one thing or 2 things more than the other one. Okay, so another really nice thing about this data set is that we have all of the weather data that came along throughout the year that's been logged. So if you want to think about how to maybe you're developing some AI perception system and you want to give it the context of what the season is and what the weather was leading up to that situation, we have all of that historical data provided with the data set. So you could think about providing that to an algorithm. It's not the kind of thing we typically do in robotics, but why not, right? A good prior and inductive bias may help you solve that problem. So think about how you could use that data. Here's a bit more of a detailed view of the main platform that we were using. So this is the ClearPath Warthog UGV. The big white cone on top is the radar dome. We also have LiDAR and cameras and quite an elaborate GNSS system. So Francois' group has spent a lot of effort to think about how to ground truth in the field. They've got multiple GNSS antennas so that they can get not just position, but instantaneous orientation from these antennas. So lots of cool work that's gone into really engineering the system to be reliable. In all, there's about 1.5 million camera images, 1 million LiDAR scans, and 200,000 radar scans that we gathered over these 4 seasons. Here's another little snapshot of some of the data, so camera, LiDAR, and radar. And you can see across even just the period of November to March, there's quite a lot of change, both in appearance, but also in the geometry. So it turns out, I think in this winter, Matej may correct me, there was something like a 3-meter accumulation of snow from the lowest extreme to the highest in our data set. And that actually changes the altitude of the vehicle as you're driving through the data set. So that's not something we typically experience in robotics. So now you have to think about how to make your localization and mapping work when the altitude of the ground vehicle is changing. We did run some baselines, of course, on this data set as well. And for example, this is a baseline from our LiDAR localization tests where we would build a map from one part of the season and then localize at a different season. And this confusion matrix tells how well we did that. Turns out we don't do very well when we build a map in the summer and then try to localize when there's been a 3-meter accumulation of snow in the winter. So lots of challenges for you guys to try to solve and make that work. And this is really just because I wanted to put the video in here. This is a video of actually stuff that we presented at ICRA last year, radar teach and repeat, running in the Forêt Montmorency. It gives you a bit of a view of what the forest looks like. So this is just a map has been built in the bottom right with radar, and now we're localizing against that radar map and trying to drive. And you'll see as we get into some of the more, like all of that twitching around, that's because we're starting to pitch and roll and our localization is really starting to break. And we happen to just manage to get through in this case, but a lot of the times that's just going to throw you right off, right? So now you need to be a lot more robust to these types of snow accumulations. Again, development kit and the weather data, I think, are some of the nice features of this data set. Okay, so that brings me to the last data set, which is the CANOE data set, which is a very tortured acronym that stands for Canadian Aquatic Navigation for Observation of the Environment. It had to be CANOE, right? We're in Canada, we like to canoe. Turns out we have 2 million lakes in Canada, and climate change is a thing. And it seems that these unmanned surface vessels would be a really interesting way to do a bit of environmental monitoring for some of these lake systems. I'm actually the lake steward for my cottage lake, where I have to go out and manually gather these water samples and mail them in. And so it'd be great if I could get a robot to do that for me. And so we built a data set to not really do the water sampling part, but think about how to navigate in these environments. So I think marine robotics data sets exist pretty nicely for open water, ports, and those kind of things. But as soon as you get into these like tighter environments with narrow openings between one area of a lake and another, navigation actually becomes really tricky. I won't talk about it, but we've been trying to build a navigation system for that for a couple of summers. And there are places where we just cannot navigate through. It's just too complicated. So we resorted to building a really good data set, and then we're going to try to develop the algorithms that would let us do that offline and then go back. So here's a view of one part of the data set. So this is actually my cottage lake in Northern Ontario. Our little USV is traveling down the lake, gathering LiDAR, camera, and radar again, as well as ground truth. We also have a section of this data set that I think would be appropriate for like environment or infrastructure monitoring. Often we hear about people using these unmanned surface vessels to do monitoring of bridges and hydro towers. So we decided to go to a reservoir that happens to have some hydro towers in it, and we drove all around those and gathered data with those. So you could think about trying to how to build 3D models and inspect these hydro towers from a marine platform with this data. Here's again a little bit of a view of some of the different routes. So we have sort of a short lake, a long lake, which is several kilometers up a lake and back down, and then the path around the reservoir with the hydro towers. And again, as I said, we have camera, LiDAR, and radar. We also have sonar. So we have 2 different types of sonar. And I think this is one of the things that really makes this data set interesting. By the way, this was a lot of fun to gather this data set. We rented this big pontoon boat and piled all the grad students into it and drove up and down the lake gathering data. So fun to get out there. Again, put a lot of effort into all of the transforms, the calibrations, the time synchronization of everything. So you guys shouldn't have to deal too much with that. That should all be done well. And I think one of the things that really makes this data set interesting is that we have data from above the surface and below the surface. So you can start to think about building some kind of a SLAM map. I haven't seen this done, where you're building a model of the shoreline and what the lake looks like under the surface of the water. And one thing I was thinking about what you could do with this data set is, could you actually try to predict before you get there and have the sonar observe the subsurface, could you try to actually predict from the shape of the the shoreline, what the subsurface geometry would look like, so that you know where it's going to be deep water, where it's going to be shallow. And I think that's necessary as you approach sort of a narrow opening. You need to think about, where is the water going to be deep enough for me to go through? So there's a problem that you could work on. We haven't worked on that yet, but I think that would be cool to do with this data set. And you've got the labels, right? Because you've got the sonar for later on when you go through those openings. Again, some things that I think the thing that really makes this data set unique with respect to some of the others, Ang's in the audience, she's got lots of cool marine data sets as well, is that we've got this sort of surface and subsurface in these freshwater lake environments. I don't think there's too many other data sets that do that. A little video of what the surface and subsurface looks like for one section. So this is going through one of the most challenging spots on the lake that we have not been able to navigate through yet. And you can see what the sonar is seeing in the bottom and what the camera is seeing on the top. I would love it if someone could figure out how to navigate through this spot. Here's an aerial view of the same place. You can see the little boat in the top left. Really what I want to be able to do is navigate through an opening like that. And if you look at the image, there's a lot of challenges there, right? There's geometry above the surface you need to worry about. There's clearly rocks that you can see below the surface of the water. There's also a lot of aquatic plants floating on the surface of the water that will confound the robot and make it impossible to go through. So you need to have this really multimodal perception system that can understand the nature of the plants, the water, the current, the wind, how deep is the water, where can I get through? I can't do that yet. I would love to be able to do that, but maybe with this data set, you guys can figure out how to do that. So that's my challenge to you. Again, development board, development kit, leaderboard, everything should be ready, hosted on AWS. Actually, the URL doesn't work yet, but it will shortly. So that's my plug for these 3 data sets. And I just had a couple of final thoughts that I wanted to put in that are somewhat related to the data sets, but also just on the topic theme of multimodal. So after building these data sets over the last few years, I really want to give a plug for radar. So getting out into these dirty, messy environments, I think it's actually, when you think about it, if you want to have robots deployed for a long time in the wild, optical surfaces, I'm starting to think, are a liability. It's really hard to keep them clean. You get dirt accumulating on them, you get ice accumulating on them. It's really challenging to really keep them working all the time. And of course, there are engineering strategies to overcome that. You can blow compressed air to keep dust off your optics. You can have windshield wipers. But my experience has been so far that those things only go so far and they don't always work. So the question is, how often are you going to want to have a human intervene to clean your optics just to be able to use these types of sensors? And then in addition, that's just, contamination of the optic surface. There's also just the particulate matter in the air in a lot of complicated environments, right? When you think about precipitation, but also dust, smoke, fog, all of these things make it really challenging for cameras and LiDARs to look through. And these are videos not from my lab, but from other people's labs in the community. We've got in the top left, Francois Parmelot's lab trying to do LiDAR odometry when there's some gusting snow. And you can see the robot actually goes straight, but the estimate goes off the straight line because there's this gusting snow that confounds the LiDAR. And there's been some great work. Steve did some great work on sort of trying to get rid of snowflakes from LiDAR scans, but this is an extreme situation, right? This is not, you're not going to be able to get rid of all of these snowflakes from a LiDAR scan because it's just gusting up all around you. On the other hand, radar can see through all of that. And in the top right, there's some videos from Costas Alexis's group in Norway where they were trying to fly a drone through a hallway environment where they'd put a fog machine, and you can see the attenuation of the LiDAR scans in that as well. And then finally, Martin Magnussen's group in Örebro was looking at these large mining machines, and they were looking at, those environments tend to be quite dusty. And they showed that cameras and LiDARs had a lot of challenges to kind of look through that type of air when there's a lot of particulate matter, whereas radar could do that really easily. So my plug is, all of these data sets that I've just talked about have radars. It's a messy sensor to work with, but I really encourage you to think about it because I think it does an end run around a lot of these problems that come along with cameras and LiDARs. And the reason is the wavelength is longer. We can also see further with a radar. You can see, I think you had some radars that could see like 8 kilometers or something, right? And the one we have is 1 kilometer. So there's a lot of range. You also get velocity information, although you can get that from LiDAR as well. So a lot of interesting opportunities with radar. We wrote a paper about the sort of renaissance in radar a couple of years ago. So you can check that out and think about it. And now all the data is there for you to try it across roads, off-road, and on a lake. And then the last thing I just wanted to leave you with, I'm probably a little short on time, but actually I'm a little long on time, but anyway, this is the last thing I have to talk about. Just an observation, not so much to do with what I was just talking about, but I think it's really interesting. Maybe this is a topic for the panel to think about, like there's sort of a convergence of sensing technologies that I see happening. So we think about cameras, LiDARs, and radars as separate sensing technologies, but how many people saw the new color LiDAR that came out of Ouster about a month ago, right? this is incredible, right? So essentially the same SPAD sensor can now image in the LiDAR frequency, but also in the ambient light frequency. So you get synchronized color and range basically like a big Kinect sensor, but on a real LiDAR that can operate outdoors in a real environment. And so the convergence of cameras and LiDARs there is very interesting, right? It means that we don't have to solve all of these really annoying calibration problems to align data from a camera and a LiDAR. Maybe we can now start to do learning across these modalities much more easily by just using the data straight off one of these sensors. So that's one convergence. The other convergence is the Doppler LiDAR that I talked about, right? That's basically taking some of the cool properties of a LiDAR and a radar and put them into a single box that you can do frequency modulated continuous wave ranging. So you get, a point cloud, but you also get the velocity like you would from a radar. And so, I kind of think the natural thing is that all of these things will converge at some point, and I'll be able to buy this amazing sensor that's the size of my fist that can do basically something that looks like a camera, a radar, and a LiDAR all at once. And ideally, it has no moving parts and uses very little power. That would be great. So for any of the sensor hardware people out there, please build one of those for us. I think that's all I've got. I just want to mention, of course, that I did none of this work, but I will collect all of the glory. These are the people that did all of the work, and these are the companies that paid for all of the work. I am the editor-in-chief of Transactions on Field Robotics, so if you have any cool work I'll just do a plug for that. If you have any cool work in the field robotics domain, please send your papers to us. We're open for business. Come and talk to me if you have an idea for a special issue. And shameless plug, lots of other stuff coming out of our lab this week, so come and check out our other talks. And I'll take any questions you have. Thanks a lot.
This is not, we can only have one quick question.
I'm only at 24 minutes. No, just
Yeah. If you have a question, please come here to this microphone.
The lightning pulse keepers get very certain about
One of the last slides with the snow coming up the ladder,
yep.
Those are clearly outliers, we could say.
Are they? I mean, if you're driving on a forest road in the winter, I think it happens pretty frequently.
No, I mean, from the sensor fusion point of view, we always work with the assumption that most of the errors are Gaussians, and then you try to eliminate anything that's not like that before they come into the sensor.
Right, but this isn't one snowflake falling at a time. These are all correlated, right? Like there's a wall of snow that's moving through the air that looks like static geometry.
My question was exactly like, what is most promising? Trying to model that and therefore not assume that the errors in the sensor fusion are Gaussians, or if you could get some pointers on where is the limit between trying to remove the outliers before they come into the optimization and instead make the optimization better and remove the Gaussianity assumption, trying to...
I mean, I guess what I'm advocating for is to switch sensing modalities, right? What I'm actually advocating for is to use a radar in that situation. I think if you had to do it with LiDAR, it's going to be really hard, right? Because, the consensus motion that you estimate from that point cloud is based on the gust, right? So any algorithm like Max Fleek or Ransack or something like that, it's all going to gravitate towards doing the wrong thing because most of the motion that you'll see is this wall of snow moving through the air. So there's not much you can do in that situation.
Building between sensor modalities.
Yeah.
Choose to use a different sensor.
Yeah, my point of that slide was to say use radar because it doesn't see any of that.
Thanks.
Okay, I think I'm out of time, so thanks a lot.
Okay, hello everyone. Let's get it started. This will be our last keynote talk today. The speaker will be Professor Sebastian Scherer. Please allow me to give a brief introduction of this speaker. Professor Sebastian Scherer is an associate research professor at the Robotics Institute at CMU. His research focuses on enabling autonomy in challenging environments, and previously that CMU's entry to the sub-T challenge. He and his team have shown several firsts for autonomy for flying robots and off-road driving. Dr. Scherer received his Bachelor in Science in Computer Science, Master in Science, and PhD in Robotics from CMU in 2004, 2007, and 2010. Yeah, please join me in welcoming Professor Sebastian.
Thank you for the nice introduction. So I'll, since we've talked a lot about motivation, I'll jump right in to the technical part. So one of the areas in my lab that we are kind of interested in and trying to explore is this idea of having a unified multimodal front end that will allow you to do, reasoning and planning. So the idea is that, doing this pre-processing, that first stage of processing is very expensive, right? And you don't want to, if you have many, you want to do many tasks with that input, right? And so if you want to do SLAM, you want to do some language reasoning, you want to do semantics, you want to do all these things with your robot, you're going to run out of things. For example, right now we are doing another DARPA challenge. It's called the DARPA Triage Challenge. And there we're doing using lots of VLMs and LLMs and semantics, and everybody has their own model and special models. And so in the end, you're like, okay, we have 20 models. They all want to run at the same time. How do we schedule all these things to run? And so the idea is to really have this multimodal input that you can then use for many different outputs. And so let me show you some first results along these ideas. So one recent work that we have is called Map Anything. So the idea is to have a set of camera inputs, but you can also additionally give it poses, depth, calibration, and so you can do many different tasks. So for example, you can do monocular depth estimation, you can do structure for motion, stereo depth, RGBD localization, dense mapping. Basically the idea is you can do all these things in one model. And here are just some more robotics relevant, use cases. So for example, the top left one was a scene at night, aerial view, or some more off-road driving view. And so here's just some more fun videos. And so you can also try this for yourself. There's a website demo. You can play around with this. And so the idea is, instead of just having images as input, you have ray directions, which is the equivalent of calibration. So camera calibration, poses, and depth as optional inputs. And then you have different prediction heads that predict your calibration, predict your depth, predict masks, like co-visibility masks, confidence, poses, and the metric scale. And so this model has been working quite well. Part of the reason is really that we have a lot of good data that we curated for this, right? Like while the model often matters, good data is really important. And so we train on a lot of metric data, instead of just visual data, because otherwise what we've seen is that the conditioning of these models is not very good. The model is also faster than kind of current state-of-the-art models. And now I'd like to talk a little bit about what we've kind of directions that we're branching out in to try and make this more multimodal than just camera-based. So one of the directions that we've looked at is this idea of NE4D. So the idea is to, in addition to just predicting the map, also predict dense scene flow. And so dense scene flow is really like a core input to many other tasks if you want to do simulation or predictions in the future. Now, to really do scene flow, we need to solve the SLAM problem and basically get the per pixel flow. So if you recall the map anything architecture, we had these inputs. What we can now add is this idea of predicting the scene flow, but also having a optional Doppler input. So you can have things like radar velocity, or if you have some LiDAR that Tim mentioned, you can also have that as additional inputs. And so with that setup, we're getting sparse 3D tracking that's comparable to sparse methods. So even on sparse point tracking, the method performs sufficient, performed at the state of the art, but is actually predicting dense flow. And so here, just a couple of more visualizations. And again, this is something you can also try for yourself. And so these dense point predictions by themselves are not that useful, right? But you can imagine that you can do other things with those. Yeah, if I had all of them on one slide, my computer broke. So here, just a couple more sports examples. And the stroller example, I'm like, this is not really a dynamic scene. Oh, the banner. Yeah. Cool. Yeah. Stroller. Yeah. I don't know. So what these methods are based on is a lot of vision transformers, right? Vision geometric transformers. And so one of the problems, of course, is speed. So something that we've been recently working on is how do we speed up these transformers? And so one thing that we noticed is there's a lot of wasted computation in areas that we don't really care about. And so, this is kind of more of a sneak peek. This is not published yet, but the idea is that it's we can do this token merging for things that don't matter. Now, based on this work, there are things, many other things to think about, right? So when you have this map anything framework, what you're doing is the number of token increases as you add more and more pictures. So eventually you're going to run out of GPU memory. So one question is, how do you do this with limited memory and have a longer map horizon? So that's something that's we're currently exploring. Now going beyond visual, one of the areas we have looked at a bit more is thermal imagery. Thermal or long wave infrared cameras are very useful because they have different failure cases than visual images. And so, for example, in rain will look different. Darkness often works quite well. Glare will show up differently. Smoke often is invisible. But if you just try to use your RGB backbone on thermal images, it will not work. So, for example, here, you're missing a detection if you just use the RGB backbone, or if you're trying to do kind of cross-modal place recognition without changing anything, it will not work. So what we do in any thermal is quite simple. So we are taking the RGB data set, the RGB pre-trained Dino V2, and then aligning it with a thermal backbone. And the way we do that is by having aligned data, right? So visual thermal aligned data, and we're trying to align the feature vectors between the two by training the thermal backend. Now, if we can do that well, the good thing is now we can actually do cross-modal matching. We can do all the things we'd like to do without changing any of the downstream algorithms. And the reason we have to do this is because the data that we have in non-visual domains is very limited, right? Anything non-visual, we are off, in sparse data land, unfortunately. And so, yeah, with that same backbone, now we can do these different tasks. And you can, if you have any questions about this work, there's also going to be a poster session tomorrow, I think. As part of this, we also developed, collected a new data set, because the existing data sets were not rich enough. And, thank you, Tim, also for adding more data, but we all need, we need more. And so as part of this, we also developed an open source kind of data collection platform that has RGB plus thermal, all synchronized, hardware synchronized together. And most important thing is it has a button. So you just push one button to start and one button to stop. If you're ever doing field robotics, that's one of the most important things. And so as part of this, we released this data set. And one of the things we show is that in the paper is that increasing this data diversity really helps with the knowledge distillation and improves performance. The other thing you can see, so we're basically adding more and more data as you go from the left to right in the three plots, and you can see that the performance keeps on increasing, meaning that we have not reached the peak yet, right? So there's still a lot to do to improve performance. So next, I'll give you a little bit of a sneak preview of something that we have not published yet, but I figured that maybe you have some interesting input on. So we currently have a big effort to collect even more data, since we've seen that this data is not sufficient. So we have set up a new payload that has visual, thermal, event, LiDAR, and radar data all aligned together. And the idea is to try and get as much data diversity in as many environments as possible. And so you can see the various inputs here. So visual, thermal, event, depth, and then also radar. I think the radar is from the bottom, so that's why it looks a little top backwards. And so, we don't really have a good data set that has all of these things nicely together in a big breadth of different environments. And so, one of the big things, as anybody who has done this knows, is, time sync and calibration is really hard, but very important, right? If you want useful data, you don't just want the data to be collected at the same time. Ideally, you want those images to be exactly taken at the same time as well. So yeah, we spent quite a bit of effort on this. And we're trying to get a breadth of environments, from handheld, biking, drone, driving, urban, rural, all kinds of environments. So there's more to come. We're currently actively collecting this data. So if you have anything that you'd like, please send requests to Parv. I'm not sure we can handle everything, but if there's something that would be useful to you, please contact Parv so we can make it useful for the community also. So kind of changing gears a little bit. So we talked a lot about the breadth of data. And I mean, once we have more of this data, right? I mean, if you think about 100 hours is still like a drop in the bucket compared to visual data. And but we ideally need a factor of 100 or 1,000 more, but we just can't handle this much. But I want to change gear a little bit to camera configurations as well. So if you think about cameras right now, the majority of images in these data sets are pinhole images, right? Pinhole camera images with normal field of view. A lot of them, I would say, most of them like 60-degree field of view. But as fisheye cameras actually have a lot of, or wide field of view cameras have a lot of advantages because you can get a lot of information in a single image, but they are very painful to work with and not compatible with pinhole models and everything that's been trained on pinhole. So a lot of current perception models actually overfit to these pinhole models. So you wanted to see what does it take to go to a fisheye or a spherical model instead that can handle any kind of camera model. So we looked at looking at projecting all the images onto the unit sphere and then redeveloping the various convolutions and operations on that unit sphere. And the idea is that you can actually you can also take your pinhole images, project them all onto the unit sphere, and now you can do everything on the unit sphere. And so so now your domain of processing, does not have to be the same as your domain of storage. So so the overall framework is you take your images. This assumes camera calibration, right? So you take your images, project them onto your unit sphere, and then you have different choices for your sampling and for your convolution. So let me tell you a little bit about those, right? So there's not one correct sampling here, but the samples in the bottom row are more uniform samples. So those are typically what you would prefer for many operations. Also, depending on what you want to do with your algorithm, you can also think about how do you want to structure that convolution, right? Do you want it to be rotation equivariant or not? So on the right-hand side here, it's rotation equivariant, so meaning that you get the same output if your image is rotated or not, which is what you might often want for, let's say, some matching, feature matching, but there might be some use cases where you actually want to make sure that you are aligned to match have the same output. And so depending on how you design these kernels, you can do that as well. And then, just to give you like a visual example of what this looks like, and it's kind of difficult because everything's on a sphere. But to have a 2D projection, you can project that image into a circle. And so once you have everything on your unit sphere, you can then do this spherical convolution and then spherical max pooling. And you can essentially redevelop all the algorithms that you have for pinhole images on spherical images. And now they work for any camera model, basically. So just something to think about, especially as, for example, humanoids and a lot of these things become popular, right? You have lots of ego-mounted fisheye cameras where you want to get all that field of view close in. Just the last thing before we wrap up, just to kind of give you an idea of how some of this perception then comes together. So when we have, here we're doing LiDAR plus camera together. So there's a SLAM system running. We create a 3D voxel map with foundation features in it. And then we use that map to, so this is what that map looks like. And then we learn a mapping from that map to a cost map using imitation learning, right? So we basically look at how do these features map to cost, and we can use that for planning. Now, one interesting thing is, what if you said, I don't want to emit anything, and I want it to work at night without visible lights. So, typically, if you have a LiDAR, right, it emits IR light, so it's very visible at night, and you don't have GPS. So, how could you navigate in that situation? So this is what that environment looks like during the day. This is what it looks like at night with brave students that themselves can't see anything and have to look at the laptop screen. And then, so here we're using only stereothermal images to then create a map. We create those same feature vectors, and then we map those feature vectors to costs again with imitation learning. And because we have the feature vectors aligned, right, between the visual and the thermal features, we can actually train on day data and use the same thing at night. The way we do the SLAM at night is using an extension of the previous algorithm, MacVio, that basically uses thermal images to then do the stereo thermal mapping at night, and then we just use that map to do the cost mapping. So to kind of conclude, our approach is to have this, try to have this unified perception system that is useful for decision making, right? And I think maybe that's one thing we should also think about is, right, when we build these 3D maps, you know, sometimes they're nice to look at and they're for inspection, but you know, it's at the robotics conference, right? You really want to build these maps for robots, right? And so what the right representation for this action is I think still an open question. And you know, one core challenge is how do we get sufficient data for this multimodal data, right? And I think this will also require more collaboration and also agreement on what we need as kind of a standard to kind of progress more, right? So there's many people doing good stuff, but it's all, everybody does their little thing, and it's kind of hard to progress as a field if you don't have some kind of standard, right? I mean, I think we see this anytime, and it's difficult because, you know, there's many different sensors, and, you know, and there isn't like an established set of sensors, right? It's like having an instrument, right? Once you have a piano, then you have a standard, right? But once you know, we don't have the piano yet. So I don't know, I don't have an answer, but I think it's maybe something we can discuss later. Yeah. Okay.
Very fast. We can have several questions from our audience. Yeah, please.
Hi, Sebastian. Thanks for the great talk. I'm curious about the future direction of SLAM. So in your presentation, there are wonderful big working SLAM and very decent and robust network system. But still, I feel that there are huge discrepancy to employ big working SLAM to this kind of weird building robotics. So yeah, I'm curious about your sense of how do we exploit this before it leads to real world?
Right. Yeah. Did we write our last SLAM paper? So yeah, I don't know. I mean, I think we still use. I think we are at this kind of inflection point. I don't know. I think for now, you know, definitely, you know, traditional methods are still very useful. On the other hand, you have these feed-forward learning methods that are getting quite good, right? So yeah, I think we are at an interesting juncture right now. And of course, you know, there's always, you know, always the hybrid approach, right? Like you don't have to throw everything away, right? Yeah.
Speaking about the sensors and making standard, recently there have been learning-based models to predict that, like depth anything in those models.
Or map anything.
Yeah. So from the robotics perspective, right, we don't care about things that look pretty, we want things that work in the protocol. What has been your experience with models? Do you think like that cameras in general are very noisy, but like this learning-based models, like probably like reduce noise, what has been your experience with this model, and do you think they're going to replace hardware?
So I think there are some use cases where you might not have a choice. Like for example, we have some drones that are 300 grams. The only thing we can carry is a monocular camera. So in that case, if you want to get some reasonable range, these models are quite useful, right? But it also depends on the task that you're trying to solve, right? So if you know, if you need a good enough guess of what depth is to do your navigation, maybe that's good enough. And maybe we should also rethink, you know, it used to be that, okay, we build a robot, SLAM has to work, and now, you know, if the robot breaks, we blame SLAM, right? So it's everybody's, you know, SLAM always needs to work, right? But I think we need to rethink that paradigm a little bit, because, you know, as long as it's, you know, we might want to trade robustness and drift for accuracy, I think. And so, yeah, so I don't know. I think these are all open questions. Yeah.
Very much for the talk, and question just about this sort of spherical representation that you brought up. So do you believe that despite the sort of heterogeneous camera hardware that still exists today, that should move to something like this, like it's sort of on the have one? And I was just curious in the work that you have done, is it tried other actions?
Yeah, so the spherical representation is a canonical representation. So you can also use it with and it can even be beneficial for a perspective camera, a pinhole type model. For example, imagine if you do self-driving or something like this, you can project all your images on that canonical sphere, and then you just do inference on that sphere once. So I think the wide field of view, especially for something like a drone, is extremely informative, right? Because you can now see a lot more, and you know, we can have lots of pixels now, but we are not very good at calibrating the edges of the fisheye. But if we could, right, that's a solvable problem, right? I mean, we can. It's just a question of skill. But if you can do that, then it's very informative, right? Yes.
Great. Let's have our outstanding speaker again.